Yeah, okay, well, I guess let's get started. It looks like sort of we're stabilized back with everyone coming back. So yeah, we're really excited to have Martin here, who's an associate professor at ETH Zurich, and has, I guess, started a number of companies, and is currently working on building products that allow us to do trustworthy, fair, and robust machine learning models. And he's going to be talking to us about certification against adversarial attacks, which is a really important area because it makes us certain that what we have is actually sort of real robustness as opposed to just appearance of it. So please take it away.
Yeah. All right, thank you very much. I just want to make sure that, I guess right now it's crossed, right? Just to check. Oh,
yes,
yeah, there we go.
We
Great.
can go slide to slide.
So I can see my slides, but not you. But I'll check for questions. So feel free to ask questions. And thanks for inviting me to this very interesting workshop. So as Nicholas said, I mean, my group's been working on this topic for a few years now, and also we have some experience through the company, which is also focusing on large parts of this space. So it's a lot of customer interaction. So some of my views are kind of also influenced by industry as well. So today, let's get to it. What I want to talk about is how to build accurate models which are certified against attacks. So on purpose, I didn't just put certified models against attacks, because one of the main challenges is actually to make the models usable and that they have good accuracy as well. It's not so hard to build a model that is rejects everything but has low accuracy. There's a lot more. This web address certification, generative models, how to enforce background priors, all kinds of things. But today I want to focus specifically on this question. So the talk is going to contain insights, techniques that cover both certification, but also training, and some of the fundamental problems that we see, and some of the open problems that I think are very interesting to look at in the next few years. So let me just give you a few examples in different application domains of what kind of certified models you may be interested in building. So if you consider this setting of visual perception, if you have something like an input image 8, you could do all kinds of perturbations to that image, rotations, flipping, brightening, noise, all kinds of things. Could be generative models-based perturbations as well. Maybe you change the weather, well, not to the 8, but to some other image. And these are possible attacks, possible perturbations to the model, to the input. And you may give those perturbations to the neural network, and you may want to classify that no change to the input 8 to the image 8 actually changes the classification. So that would be the verification problem. And the attack problem would be like finding an 8, some perturbation and parameters of the perturbation where the 8 gets misclassified. So the verification generally either succeeds or it fails and gives you a counterexample. Now the trouble with this verification situation here is that it's actually quite difficult to, next to impossible to, to brute force enumerate all the perturbations, except in very, very restricted cases. For instance, if you're dealing with geometric perturbations, you have pretty much arbitrary compositions of translations, rotations, shearing, all kinds of things you can do, which can be composed with noise, with flipping, and potentially infinite number of values for the parameters. So you cannot really enumerate, and the standard solvers like mixed integer linear programming solvers or SMT solvers, which have been used, especially SMT in verification and security verification, are not so effective, largely due to the non-linearities that occur in the network. All right, here's another example. This would be an audio processing. So you have an input signal, some recording of someone's voice that pronounce the word, for instance, stop. And you'd fit that signal to some pre-processing normally, which processes the input and then feeds it to some neural network, maybe LSTM, maybe some RNN. And the goal of the network is to classify the pronunciation as the stop label. You can make attacks on the input again, changing the volume with which you speak. So, for instance, more quiet or more louder, and have the network misclassified to go. And there was a nice early work by Nicholas on this topic, pointing that this model is actually not so robust. So this is another kind of setting. So a goal for a certified model here could be to prove that to build a model where you show that the change in volume up to some decibels, up to some change in the volume of this loudness of the voice does not affect the classification. Okay, so you may have such a challenge here as well. In terms of natural language processing, you have a similar situation. If you have like a sentence such as like perfect performance by the actor, and you have a sentiment analysis, it's positive, you may insert a synonym here, replace perfect with spotless, and the model maybe some transformer model or some other natural language processing model, and now classifies it as negative. So this is kind of actually not so difficult to do by just enumeration, by just trying out all the synonyms. But with more complex sentences, something like no reason for anyone to invest their hard-earned bucks into a movie, which obviously didn't invest much into itself either. There's all kinds of different synonyms for the different words. So over here, actually, for this sentence, there is, even not being so creative, there's about 23 million sentences generated by the synonyms that you can replace, for instance, bucks with dollars, and movie with film, anyone with everyone, and so on and so forth. If you just do enumeration, this may take between 10 and 30 minutes. If you actually add longer sentences or more synonyms, this may be actually even harder. So your goal here would be, to certify. So your goal here for a certified model, if you want to build such a thing, you may want to build a model where you prove that the replacement with synonyms does not actually affect classification. It stays positive. All right. So just to give you the high-level view of, these are some examples of settings where you may care about, about certifying the model. There are many, many others involving generative models or other domains, medical imaging or financial predictions. So there are two steps generally that the community has investigated over the last 4 or 5 years. So two ingredients when certification and building certified models. One is step one, which is the specification. So specification tries to capture this attack space. So for instance, changes to the image, right? So over here, changes to the image A, could be some infinity bow around the image, which captures the noise that you can introduce to the image, or it could be some symbolic range on the parameters of the transformation. That could be like for the image setting. For the natural language processing setting, it could be that there's no annotation here, but you follow. If you have the sentence something like fire is cold, and you have, for fire, you have two synonyms like bonfire and blaze, and for cold, you have two synonyms like chilly and frigid. You may take the embeddings of these synonyms here, so there are 3 of them, and then you can put a region around them. So here we see in the right column 2 regions, and in these squares, and these 2 concrete points with the x's, and together they form some kind of symbolic representation of the sentence, which captures all the possible synonyms that we care about, and potentially more synonyms and more other points in there. So the first part in all this certification typically involves representing the specification in some way, oftentimes in some symbol. This representation could be convex or non-convex set, could be a generative model even. And so once you have that, once you have this region, the specification, which captures the attacks that you care to certify your image against, in the second step comes the verification, which tries to prove that all of the points which you have inside the symbolic region actually classify to the same label if you care about robustness. Okay, and so these are generally like the 2 steps that that's how certification and building certified models goes. And I'll prefetch a bit the discussion here and tell you that there's been a lot of work in step 2, and we'll discuss it in the talk. But we really need a lot of more investigation in step 1, capturing interesting specifications. For instance, those of you who know about the ACL checklist, people are trying to write some kind of interesting robust specs. Okay, a couple other points about verification here. In these particular examples, as I showed you in the previous 4 examples with audio processing, geometric, NLP, and so on, you cannot just enumerate these points inside this symbolic region. It's just usually infeasible. And so when you talk about verification, there is 2 points. So one is that oftentimes, like in the audio processing or in the geometric transformations or in other settings, you have some kind of pre-processing before you actually invoke the neural network. And so you need to also deal with that. You cannot just talk about neural networks only. The second point is the kind of guarantees that verification gives you. Is it deterministic guarantees? or is statistical and probabilistic guarantees where you provide bounds and guarantees with some confidence, maybe with some certainty of 99.99%, but still statistical. So examples of this would be randomized smoothing or statistical verification that many people have looked at. We've also looked at this. In this talk, I'll talk specifically about deterministic certification, where you have basically 100% guarantees. And the two methods are actually quite complementary, and there's a lot more to be done at the intersection of this. So anyway, these are the two steps. And what I want to tell you now is some of the challenges, not just with step 2, but with how to build models that you can actually certify against attacks, and more generally, proof robustness properties and other safety properties about them. I want to remark a point here, which I think will come up probably in the panel if I'm around just to watch it, is that this area of building certified models, in our experience, in my experience at least, is a very technically rich space. And the reason is that it tends to involve 4 different dimensions: optimization, sampling, statistical guarantees. Then you have abstractions, which is something we're going to look at in the talk. Essentially, how to represent infinite behaviors. And then you have projections onto surfaces, which are very important. And then you have logic. So, the whole area of how to build the certified models is in some kind of a intersection between continuous reasoning and symbolic reasoning. So it's just an instance of this intersection, which I think is going to be more and more important in the future. Now, a few years ago, when we started looking at this problem of certification, the first thing that came to mind was, you have deep neural networks. Deep neural networks are essentially affine transforms with particular kinds of nonlinearities, not general nonlinearities. And at the same time, in the whole security programming languages space, there's been huge amount of work on automated reasoning, specifically in a style of abstract interpretation, which is a theory that's been invented in the late 70s. And virtually, pretty much all automated analyzers can be seen as abstract interpreters of some kind. And there is a sub-area of abstract interpretation called numerical abstract interpretation, which deals particularly with numerical programs. And so the intuition was, well, why not just, instead of inventing new things, why don't we just apply this theory and this numerical relaxations that people have developed since the late 70s. And this is what we did. 3 years ago, we had a paper at SNNP in Auckland called AI2. And the idea of this paper was specifically that to directly and somehow facilitate the application of abstract interpretation to this problem of proving properties of neural networks. So let me give you the high-level intuition. But just to remark here, essentially what happened was to connect the two worlds of deep learning and numerical abstract interpretation. The idea was to take the neural network and compile it down to a program, just a regular program, which standard abstract interpreters could understand. So in some sense, we didn't invent new relaxations. We didn't invent like a new reasoning methods. We just connected the two areas and showed how to connect one with the other. And so the high-level idea of this connection was that you'd have your input shape here that you see this hyperbox, which is described by some symbolic formula. You don't have to worry about what's written here symbolically. It's a particular kind of relaxation. And then rather than thinking concretely in terms of concrete terms, like pushing the image 8 for the network, you think in terms of symbolic terms. You work with symbolic images essentially, which capture potentially an infinite number of perturbations to the original input 8. And so rather than pushing concrete points for the network, you push these symbolic regions for the network. Okay, so you take that symbolic region and then you push it for the network, for the first layer of the network. And to push it for the first layer of the network, you need to define, you need to change that, you need to define how common activations and transforms like affine transform, ReLU activation, or sigmoid, or whatever activation the network is using, transform these symbolic shapes, right? And so you lift the concrete definitions, the concrete functions to symbolic functions, and you define them, which can be quite tricky. And so this now abstract transformers, as people call them, or symbolic transformers, just take symbolic inputs and transform them to some other shape which captures essentially an over approximation of the set of possible inputs in this hyperbox. And so you push it through like this to the next layer. So each of these arrows that you see is just an abstract transformer, abstract version of the layer that propagates, it works on symbolic shapes, symbolic concrete inputs. Then you get to the output shape, and this output shape essentially captures all the possible results that could have resulted from running any of the possible inputs in the hyperbox, and potentially more. So it may have false positives. And then using this output shape, this funny output shape here, you prove your property on that output shape. And if you succeed to prove the property on that output shape, everything is good. If you fail, it could be that there is a counterexample in the input. There is truly some input in the region which gets misclassified by the network, or you have a false positive. So this was the general scheme that since then I think most people have adopted. But what has happened over the last 3-4 years, well, since this paper, is that essentially people in different places around the world have developed custom abstract transformers for pushing the symbolic shape. So rather than having it generic like in this paper, things became very custom to the particular domain of deep learning. And so let me just summarize to you, kind of in a slide, what that means. So we can summarize many of the advancements, including some of the advancements that made in our group and other groups, as follows. So this region here on the left that you see, the blue region, described by some constraints. You don't have to worry about the constraints. Some kind of convex shape, some kind of restricted polyhedra shape, some intermediate layer in the network. So it exists there. And then your goal is to transform that shape into some output shape by the ReLU layer. Okay, so you have like two maxes here that we need to propagate. And so you do that, maybe you'd get another shape. And many of the techniques that you see these days and that are popular and work well are essentially working in the single neuron mindset. So they say, look, to compute the constraints for the neuron Y1, I'm only going to look at the neuron X1. And to compute the constraints for neuron Y2, I'm only going to look at the constraints for neuron X2. And then, these constraints that I get here for Y1 and Y2 are going to form my shape, and then I'm going to continue downstream with the network. So that's how, the high-level idea of many of these, transformations. And this has the advantage, of course, that if you're working in parallel, like on a GPU or some other parallel architectures, you can parallelize the computation for Y1 and Y2. They're independent, essentially. And they only depend on the shapes of the constraints associated with one input neuron. So that's kind of the high-level summary, and I refer this, abstract transformers, or these lifted activations, which transform the symbolic shapes, as single neuron, because they kind of look at a single prior neuron, like Y1 constraints only look at the X1 constraints. So just to give you a little bit of a more visual view of what happens here, if you compute the shapes for a single in the single neuron way for the ReLU activation. So your input neuron X, suppose that it lies in some range lower bounded by L of X and upper bounded by U of X, so some interval, okay, which you can compute from the constraints associated with X. And then in this particular case, what you see is, in fact, one of the most tricky cases that these analyzers have to deal with, which is the so-called crossing ReLU, which means that the X can take both negative and positive values. And then what you want to do here is to approximate this green line, because in this particular case, it's a non-convex shape and it's hard to work with it directly. And so if you want to approximate it in the single neuron mindset, as good as possible with convex shapes, you'd come up with a triangle. So there was a paper on that. Unfortunately, the triangle is, for various reasons, it's not efficient to work with. It's quite inefficient. So this triggered people investigating different kinds of approximations for capturing this green these green lines. So here's some examples. You could have the box relaxation, You could have something called the deep zonotop relaxation. And so these are all examples of different convex shapes. We just approximate this green line. And of course, they include many points which actually cannot happen in these blue regions. Okay. So lots of work, lots of concurrent work. We did some work. The group of Zico Coulter, Eric Wong also did some work in ICML. Wang et al. Did some work. Huan Zhang did some work. And many other people actually came up with this kind of approximation. It's a very active area of trying to figure out how to actually come up with this convex shape, so that you don't introduce too much of this blue region, but you also don't. You're also efficient, so that you can compute them quickly. One thing that you will notice if you look carefully, for instance, in the deep zone relaxation on the bottom left of the screen, you'll see that there's actually pretty much an infinite number of those shapes, because we can just pull the right hand down of the shape and pull the left hand up, so you can kind of twist it like that. So essentially, learning the parameters of the approximation, how the shape looks like, is also kind of like you can learn what the best what is a good approximation for the particular input. So anyway, there's been lots of work on this, different kinds of approximations like that. These are some of the most effective ones that have worked well in practice that I'm showing you. And this triggered a nice paper by Salman and others at NeurIPS 19, which was called the convex barrier relaxation paper to tight robustness verification. And what it tried to do is kind of systematize a lot of these relaxations, which is very nice. And it conjectured that the tightest relaxation that you can get is this thing with the triangle up there in the middle in the middle column up top. And it is kind of correct if you're looking at it from a single neuron view. If you're looking at it from the not a single neuron view, and that's why I showed you the single neuron view, just so that you know what this is. But if you don't look at it from a single neuron view, you can do better than the triangle. So if you look at the shape on the left here with the gray region, you have these two input neurons, X1 and X2, whose constraints form this twisted square. And so obviously the constraints for X1 and X2 are related, otherwise you just get the boxes. Now, if you do the triangle approximation for Y1 and the triangle approximation for Y2, and you put the shapes together, you'd get what's shown up top here in the blue region. If you do something better by considering both X1 and X2 together, so you do like a 2-ReLU, not like 1-ReLU, so not like single neuron, but 2 neuron, if you like, you'd get a shape which is than the one up there. And so a lot of the interest now in building verifiers for automated verifiers for neural networks revolves around these clever combinations between multiple neurons and how to trade off. Obviously, if you consider too many neurons, like X1 to X50, it would not scale very well. But if you consider too few, you may be too imprecise. So people are trying to figure out ways to kind of look at multiple neurons at the same time, but restricted groups. And this can have a very profound effect on the overall verification precision and scalability. So we actually implemented a lot of these techniques in a common framework called ARAN, which takes as input a neural network, some precondition which captures the attack space, and the postcondition, some property you want to check, for example, robustness, and then it implements all of these relaxations and runs them, and you can select which one to run and check your property. There is a competition that some of you may be interested in, maybe not, but I think it's good to check out, potentially contribute to the competition, called V20. And this year, again, there is a competition associated with CAF, where people are running different verifiers, and we have different benchmarks. And people are trying to figure out what kind of properties, what kind of verification methods work well. So I think this is quite interesting, and I'd say we're still in the early days of trying to figure out where verification works. And so I think that's what I wanted to tell you generally about verification, just so that you don't get the idea that this works just like on noise introduced to the input, like some L infinity boxes or some hyper boxes. You can apply the framework to, for instance, geometric transformations. So if you have something like, you have a rotation by 30 degrees of an image, you may say, I want to prove that no matter how I rotate the image between 0 and 30 degrees, the classification is going to be the same. I cannot attack the image in any way. And then what you do is you look at the rotation function, and you cannot enumerate here because you're dealing with interpolations like bicubic or bilinear interpolation. So you have a basically unbounded space or very large space of possible values for the pixels. And so what you do in this way that people are looking, verifying properties, you take this rotation function, which includes interpolation, and then you summarize the effect of the 0 to 30 degrees into some symbolic region, potentially an over approximation of all the possible rotations between 0 and 30 degrees. And then you end up with a shape, and then you just call a run or some other verifier that you like to verify that any point in the shape is actually classified to free. So this would be an example of how would you actually use it. All right. So this is the part one I wanted to tell you about, just a high-level idea how this certification works, and to tell you what the problems are, which is essentially multi-neuron abstractions. I'll discuss a little bit more on that towards the end of the lecture. Now, the problem is that if you are just taking networks that are normally trained, standard empirical risk minimization, you're not going to be able to prove much on these networks, whether it's robustness, whether it's some other property that you care about. And so one of the problems that is very important for making certification succeed is actually building networks and models that you're more able to be certifiable, let's say. Okay. And so started working in the certification space. This came up as a natural problem. And so what we thought is, let's try to, just in the way I showed you how you connect abstract interpretation with neural networks, let's try to connect normal optimization with abstract interpretation. And so there was this work in ICML 2018 by Matthew Meerman, Tim Ongier, and myself, where we essentially did differentiable abstract interpretation. And the idea of this method is I think very simple. And essentially what it does is it does exactly certification going forward, but you're not proving anything. You're just taking your shape, you're pushing it through the network for these abstract transformers, and you get some shape. In this particular example, you get some shape. Your input region could be like this region S of X, and then you push it through, and then you get some output shape called M sharp S of X. M sharp just says that the model M, which are these layers, and sharp just stands for the fact that it's abstract layers. So you get some shape, which is called M sharp of S of X. That's fine. So there's nothing new here. This is exactly what you do in the certification. But now, rather than prove anything, what you want to do is to say, well, how do I change the weights in the network so that, if you want to think about it, I want to make the shape smaller. Because if the shapes are smaller, I'll have less over approximation happening in the shape, less false positive will be able to prove more. And so this kind of intuition is expressed on the optimization problem on the right, which is essentially adversarial training, but with abstraction. So what it says is just says, well, find parameters of the network. So find parameters of the network theta, which minimize this worst case behavior. And what is this worst case behavior? Well, this essentially means taking your abstract shape that you see at the end of the analysis, this M sharp S of X, and finding a point inside the shape or on the surface of that shape, which makes the loss behave as bad as possible. And once we find that shape, once we find this point which makes the loss behave as bad as possible, we want to change the network weights so that it makes it behave better with respect to this point Z. And then we continue this process. So if you look at adversarial training, normally adversarial training tries to inside S of X that makes the model behave badly and tries to change the weights. And certified training, you try to find points at the end of the abstract shape that you get at the end and to change the weights. So that's the high-level idea. So this essentially allows you to plug in any symbolic propagator for the regions and solve this optimization problem. So that's that. And the problem is that, so there was lots of work on this following this paper. I think also by DeepMind picked up these methods, and they focused specifically on the box relaxation, and also made some optimizations that made the results better. But this is the general method. Now the problem is that if you apply this method as this, right, and we applied as this, other people applied as this, and I think it's quite interesting. But the best results that you'd get on something like CIFAR10 with this relatively small L infinity region around the input would be like an accuracy of like 70% and certified robustness around 54%, which essentially means, if you look at your test set, 70% of the samples got classified correctly, and 53.9% of the samples got classified correctly, and you are able to prove them robust as well. So certified robustness is necessarily smaller number than the accuracy. So this is a fairly useless network of 70% for CIFAR, where the accuracy is way above 95%. And the fundamental question is, why is this happening? Why you're not able to get higher accuracy? And certified robustness is pretty good, but the accuracy is low. And one hypothesis here, which is interesting, is that in theory this method allows you to plug in more and more tighter relaxations. So you can start with box, which is very simple. You can make it more refined, more tight, and so on. And you'd be hoping to get better results because you're introducing less garbage in this intermediate shape, less false positives. But it ends up oftentimes that you actually get worse results, which is very non-intuitive from an analysis perspective. How can you get something that is better but produce worse results? And one of the reasons, if you look at this formulation of the optimization, is that you're actually differentiating not with respect to the concrete functions, affines and reviews and whatnot. You're differentiating with respect to these complicated now abstract functions, which are much more complicated abstract transformers. And so the hypothesis here is that more complex abstractions actually lead to more difficult optimization problems. The surface, the loss becomes much harder to optimize, more discontinuous, more sensitive to changes in the weights, which makes gradient descent work not so great. And so we have this paper, that's on arXiv, about why is it that tight is a paradox of sorts. Why is it that tighter relaxations actually hurt certified training? I encourage you to take a look because there's been a lot of work on using this optimization method, and it works in some cases very well, and in other cases not so well. We're still trying to understand why. What is the potential path forward? What you need to do is we need to think about how to produce simpler optimization problems where we don't differentiate for the code of these complicated abstract transformers which are manipulating symbolic shapes. And so this is one method that we reached after a lot of thinking, which I think at the end is actually can be explained the whole method in one slide. It's a very simple method, I think. And it's an oral last year at ICLR. I think it may not be the definitive method, but I think this is kind of like the promising direction to start thinking about how to generate simpler optimization problems. And the high-level idea is actually quite nice. Is you get your symbolic shape again, and this time rather than pushing it to the end of the analysis like before, you push it one layer for this layer H1, so you get this dark blue region here. And then what you want to do is you want to say, well, let me find the point in this dark blue region which makes the loss behave badly. So I'm trying to find this point inside the region, this region here, this region S1, and so I may find some point X1. And if I'm able to find that point, then I can train the network, the subsequent layers, H2 and H3, to minimize the effect of that point X1. So essentially what you're trying to do, you're at the point in the network and you're saying, well, let me try to mitigate the effect of the point X1 on the rest of the network. So when I push it through, things are good. Okay, so one way you can think about this is that you are doing adversarial training, essentially generalized adversarial training, not to work only at the standard adversarial training, not to work only at the beginning shape, which is this hyperbox with this image 8, but also to shapes that arise in the middle of the network. So adversarial training works in the beginning, like PGD training. Certified training works at the end shape. This thing works in the middle. And the nice thing is that it doesn't actually require abstract transformers. You never have to differentiate for abstract transformers, because you take your dark blue shape, and now you're saying, find me a point x1, which makes the loss behave not so good, and mitigate its effects by changing h to h3. Once you're done, you push that shape through the layer h2, you get another shape, and then you are again trying to find a point inside this region s2, which mitigates, that makes the loss behave badly, and then you're only allowed to change the layer h3. So you go like this in sequence and freeze the prior layers and only work on the subsequent layers, and you never care about the transformers which have obtained this layer on which this shape on which you're working currently. So I think this is an interesting direction. I expect to see like more work in this kind of direction, generating simpler optimization problems. So just to wrap up this talk, so I want to give you some general thoughts on what's next in building certified models. There is it's a very broad space. There's many works, but kind of like the general themes. So in terms of specification, so far the community has considered mostly this L-infinity norm, other norms, and I think at least in my experience in the companies and in industry discussions, L-infinity is not exactly something that companies care about, but it is a very important property, a uniform property for core advancement in the verification space, and being able to compare the different techniques, because otherwise, just comparing on completely different specifications doesn't really make sense. So this case, L-infinity may not be so practical, but it lets you build verifiers, good ones, which actually work on more practical properties, potentially like geometric transformations or generative models or audio or other kind of things. But in general, we need more semantic properties, we need more temporal properties, we need probabilistic properties, and so on and so forth. So that's, I think, a lot more work needs to be done in the specification space, not just the verification. In terms of verification, it is deterministic verification. I think that the way forward is in these multi-neuron abstractions that kind of like try to transform shapes involving multiple neurons, not just a single neuron. There will be a lot more combinations with mixed integer linear programming solvers, testing methods, and custom GPU integrations. So our experience, for instance, in some of these relaxations is that once you have custom GPU implementation, which is non-trivial, you can get 100x, 1000x speedups to the point where actually it makes verification scale to pretty large models. We also need much more investigation into non-linearity, not just convexity, but like some limited forms of non-convexity. So that's some thoughts on verification. In terms of applications, I think so far people have focused on classifications, because even this is a hard. Even binary classification, is like 10 class classification with the digits and CFAR 10 and whatnot, is still pretty hard. I think people are starting out, people started looking at generative models, different kind of applications. And I think that this is something that one has to be careful here, because what's interesting here in the verification is that when you pick a particular network architecture, so for instance something like LSTM, if you're working with these convex relaxations, you typically don't want to just make convex relaxations one for tanh, another one for sigmoid, because they may not work as well as having the convex relaxations that combines tanh and sigmoid together. And so these custom architectures tend to bring particular combinations of activations and particular ways to construct the networks, which which let you be creative in making abstract transformers for compositions of different activations. So that's our experience in basically NLP and whatever we look at the new domain. So I think in that sense is interesting. And down the line, thinking about how to actually automate the process of building the relaxation so that you don't have custom ones all the time appearing. I think we'll see more in the loop end-to-end tasks, like the geometric and the audio processing. These are not really just neural network tasks. There is some functions that are transforming your input or normalizing it or doing some pre-processing. So you need to worry about that. So in terms of scalability, scaling verification, scaling it to properties, robustness, or certification against attacks, or just general properties, I think verification alone is not enough. You need much better training techniques, certified training, to produce simpler optimization problems. And I think another thing we need is, which is kind of fundamental problem, is to deal with compositionality. When you're doing certified training, whether it's enforcing properties, whether it's randomized smoothing, or whether it's like the techniques that we looked at today, this min-max optimization problems, you typically focus on a single property like robustness to noise or some attacks and whatnot. But we don't know how to actually work with compositions of different transformations. If you have a model that's robust to one thing and you have a model robust to another attack, how do you actually put them together? Because maybe you'll be able to build a model for like hard-coded 5 attacks, but what about some other thing? So compositionality somehow is not well investigated. Another thing we need is to be able to somehow, what I say is continually benefit from verification regardless of how good the verification is. So what this means is, if I'm doing certified training, which is very intrusive, if I'm doing verification, and I'm stuck to working with small to medium networks, how am I going to help someone who is working on like large transformer models or large visual models? How we do this? And so I think this is another direction that's very important. And this is something, and this is my next to last slide, is this question which bothers me, is like, how can verification advances benefit large scale networks like that people are building in industry, in practice? And I think we need to move towards compositionality in some sense. So this is a paper I think in ICLR that I think it's also in this style we need to start working. And so basically the idea here is that you have a small certified networks which you have built with certified training, verification, whatever kind of thing you want, deterministic verification, statistical, doesn't matter. Those networks typically affect the accuracy in some way. They make the accuracy smaller and raise the satisfaction to the property you care about, like robustness to adversarial attacks. But then you have normal trained networks which don't care about the robustness to anything. They just care about standard natural accuracy. So you have these two worlds. So how can I help those people on the world where to extract some robustness benefits without like retraining everything from scratch? And so this is this idea where you kind of put them together via a selector, where for every input you decide whether to go to the certified network or you want to go to the big non-certified network. I'm not going to go into the details, but I think what's interesting here in the numbers is I think it's very early for this kind of work, but I think that's where I think things should go. If you look at something like let's say ACE, that's what the method is called. So the third column here is the method of producing the network. So this technique is called ACE. So if you look at ACE ImageNet 200, you get a natural accuracy of 70%. A PGD accuracy of 60% and certified accuracy of 3%. Now, certified accuracy of 3% is not, certified robustness of 3% is not very high, but look at the next best thing that you actually get to the existing state-of-the-art methods like ClearPower, where you completely kill the natural accuracy, like 27%, even though you get 15.9 certified accuracy. So what this ACE starts letting you do is to plug in large big networks on the right, this HT, and use these small certified networks on the left. So I think this is a direction which is also worth exploring, so that you can encapsulate all these advancements in verification into their own box and be able to benefit from them when you're working. You have large networks and someone still cares about certification. And you can see the benefits here on CFAR10 when you start getting, start getting much better natural accuracy and still get some certified robustness, like 22-23%. So anyway, this is the direction which I think is interesting to think about. So in the course here, in the lecture here, we discussed some of these techniques, and to give you a little bit of a flavor how things go, we actually have a full-fledged course at ETH on these topics, all these topics from statistical verification, certified training, fairness, all kinds of things. It's a full-fledged course, so it's not just like papers, but also exercises and all that. So it's actually public. This year we made the lectures public on YouTube. It's attended by quite a few students, graduate students from different areas of science, like computer science, math, robotics, and so on. So if you're generally interested in this space, you can go and check it out, and may allow you to get up to speed much faster than just going for the papers, where especially in the certification space or in certified training, there is a lot of machinery that may be harder to parse than just going and looking at the lectures. So this is what I wanted to tell you. Hope you enjoyed it, and happy to take questions. Thank you.
Thank you very much. Virtual round of applause. Very nice talk. While we wait for people to have a chance to ask questions in the Q&A, and please do so, I figured I'd start with one, which is that so we know, so in other areas of security, let's say cryptography or something, where we have certified things, the probability of failure is essentially 0. But like the best deep learning models we have, like even in benign accuracy, have like, let's say, I don't know, 98% accuracy or something high, but it still has like a 2% error rate. So like, how do you see certified models? Like, what do you see the use of certified models? Like, given that we're probably not going to be able to certify 100% accuracy.
Yeah, I think to me, what I see is that a lot of this, not being robust and to kind of obvious perturbations, and whether these are what I see, I think in practice that will happen is that people are trying to figure out what the specification is, and more and more there's going to be custom specifications, either via some kind of generative model or via some kind of a language which captures the attack space or the robustness that you're interested in. And so I feel what's going to happen is somehow there are two views here. So one is this robustness of the model, and one is this adversarial robustness of the model. So in the these are kind of very different view. Like in the adversarial robustness, as long as there is like even one very low probability attack, you may be already not accepting the model. So certification. It could be that it's not certification may not be able to let's say to prove 100% of the you can use certification to prove against whatever attacks that you have, but it may not be able to prove all of the possible robustness properties that you care about. So I'd say this in terms of adversarial robustness, I think there's going to be properties that people want to certify for certain. So for instance, if you look at like ACAS network, you have pre-post conditions, and people there have it pre-post and they want to certify it. So I think there's just going to be domains where you really want to certify it, and then there's going to be domains like this robustness, just pure robustness, where people are going to be writing kind of like ACO checklist kind of properties, where from what I see in industry, people are still trying to figure out even what the metric is. So they want some assurance, whether this is experimental robustness, whether it is certified robustness, still trying to figure it out. But I think it's a good question, whether 100% satisfying certain properties, backdoor or like robustness is something that from a security perspective makes sense.
Yeah, I guess it's just like, I mean, given that we can't even get the clean accuracy to be 100%, it seems like we're not going to have a chance of getting the certified accuracy to be 100%.
Yeah, I think where the research will go at the end is that you try to get the certified accuracy as close as possible to the clean accuracy as some measure of robustness.
Yeah.
Some metric. I think if you are able to get 98% accuracy and able to get 95% certified accuracy, that's probably as good as you'll get, and that's what people I think are trying to figure out how to do. Yeah. That's why I see where the robustness certification going, specifically about robustness certification, how to build such models. But in practice, what I see is that people are coming up with their own specifications, that they really want to make sure the model is robust too. And there's one more thing which I didn't talk about, which I think kind of relates, is that notion of probabilistic attackers. So if you look at a lot of the stuff on robustness certification, everything is equally likely, essentially, which actually in practice is not what happens. So you have some probabilistic model that tells you which transformations are more likely, and you want to have certification with those that are more likely, and maybe you care less about the transformations attacks which are less likely. So this I also see happening.
Yeah. Okay, there are a couple questions from the chat. Let me start by asking one by Rob, who says, there are times when companies use machine learning techniques to do authentication. So maybe Apple learns to recognize your face before giving access to the device. It would be nice to have more robust techniques that are in line with the crypto model. I guess the question is, what are your thoughts on this kind of certification?
So let me just, because interrupted. Is it written? I can read it.
Yeah, it's written in the Q&A. Like there's no question mark at the end, so it just says sort of a comment that it would be nice to have that things that are more in line with the crypto model. I'm guessing the question is, what are your thoughts on this?
I'm just trying to understand what the question is exactly, but yeah, I mean, I think that they're just they're just particular domains where certification will make sense. But I'm trying to understand exactly what the question is.
Maybe we'll come back to this. Maybe Rob, if you want to try and rephrase your question, maybe that we can go to the next question, which says.
I'm trying to read it. I'm trying to read it here. I don't know what it is, but it's in the chat somewhere.
So if you, on the right-hand side, there's a session tab. There's a chat on the left, polls, people, Q&A on the very right. If you click on Q&A.
Q&A. Sorry, I was in the chat.
Yeah. Let's move on to the next one while Rob maybe rephrases. And this question is maybe a little simpler, which just says, what are the verification challenges for the image segmentation task?
Yeah, we actually looked at this. I think it depends on what kind of method you're using. I think if you're looking at this method here, there are two challenges, like the deterministic certification. One is in the there's essentially three, but one is in handling the kind of activation functions that happen in those models, and one is in handling various metrics, like people use it's not just classification, this intersection over union and so on. So different properties that you may want to. But to me, segmentation, for instance, if you're looking at deterministic certification, this would be how do you define custom convex relaxations for a particular combinations of relaxations used there, and which tailor to the particular metric, like intersection over union or some other metric that's being used. That would be the natural thing. At least that's what has happened to us when we looked at particular application domains. You start with like a basic certification, like here, the base certification of basic, and then you figure out that there is particular combinations of activations where it's losing a lot of precision. Then you try to design custom relaxations. So you need to look at just the particular relaxations the particular activations that people are using there, and then define custom transformers for those. That would be one thing.
Yeah, that makes sense.
For the statistical certification, there is other chance we actually have an upcoming paper in ICML that does smoothing for Yeah, image segmentation, different segmentation tasks.
Okay, so there's another good question, which says, can the certification training be done in the black box setting with no access to model parameters?
Yeah, good question. I was thinking about it yesterday. So, yeah, I mean, this is a that's a very interesting question. Not the current existing schemes, which of course need access to everything, but I think there is a problem, which is if you actually, I mean, if you actually take certified training, and you know how do you do it in a black box setting? One thing you can do is you can learn. You have a lot of white box access to certified training. You may want to learn like a black box version of the certified training by teaching it on a lot of these white box certified steps that you are changing the weights. So think of a policy that tells you how to change the weights, which is trained on the so the only thing you'd essentially be able to do is to change the input so that the weights are changed. So essentially you're learning, because you don't have access to the weights, you only have access to the input and some black box training procedure. And so you would essentially learn a policy how to change the input to simulate the changes that the certified training does. Ultimately, you need to learn a policy that simulates certified training. I think that's very interesting. So that's exactly the question I was thinking about yesterday. So let me see this. I hope that answers the question, but let me see this other one. Is there any other ones, or because I'm? Hope I cannot hear you very well, Nicholas. Oh, yeah, you went. Now you're. Oh no. You somehow went mute.
Yeah, okay, sorry. My mic has a mute button that I managed to press accidentally. So I guess if you want to try and read Rob's question and maybe see if he rephrased it up top, that certification gives guarantees of correctness and crypto gives guarantees that are like orders of magnitude better than one, or orders of magnitude better. First, is it possible, appropriate to compare? And second, what's the right way to think about sort of this this connection?
Yeah, I think I mean, so I have several thoughts on this. I think crypto. So basically, what the thoughts I have on out of this is that if you look at cryptography, if you look at security in general, and there is techniques, and in general program construction, you have cryptography, and there is a way to construct these cryptographically secure schemes, and then there is against essentially arbitrary attackers, and then you have program synthesis, program derivation schemes that people have worked on like the last 40, 50 years. But in terms of neural networks, what I think is missing is the theory for actually constructing models that satisfy properties, because everything gets piped for the gradient, essentially for optimization. So I actually lack this theory. So that's actually a fundamental. If you look at security, many works on cryptography stuff, many works on like formal verification and whatnot. But all of this have a method for constructing programs that satisfy properties or computational protocol. But with these models, we don't actually have a theory to do this in practice. We just rely on a gradient descent optimization of some kind. And this I think is where a lot of the research has to go in kind of constructive theories for constructing models, not universal approximation stuff, but kind of more practical things to construct models that satisfy properties. I think this is what's missing fundamentally. That's why we're getting into adversarial attacks, or like not satisfying properties, or logic to losses, and all this kind of stuff.
Okay, no, thank you very much. Yeah, so thank you again for the time. We're now going to move on to the next session. And great, we have a next session chair here. And we're going to, is the speaker for the first paper here? And I guess, Nick, please take it over.
Yeah, thank you, Nicholas. Okay, all right. Thank you very much for accommodating. We see office space, that's encouraging. We haven't seen office space for a long time. Can you also check if you can share your screen? So the Mohammadreza from University of Arizona is going to talk about binary black box attacks against static malware detectors with reinforcement learning in discrete action spaces.
Yeah, sure. Thank you, guys. Can everyone hear me? Because I'm sorry, this is my first time using this tool. I'm not very acquainted with it. Yeah.
We can hear you.
Awesome. Awesome. I'm just going
But
to
we
try
don't
to
see your
share
screen.
my screen.
Yes.
Okay. I'm just going to try to share my screen. Okay. Entire screen. And okay, can everyone see my slides?
Yes, we can see.
Oh, awesome. Awesome. Okay. Okay. Thank you, guys. It's a pleasure to be here among you guys for the second time. And I really enjoyed the talk in the beginning of the session, especially the Q&A. And it's kind of, I think it's a great segue to this one because I asked the question about the black box setting of how we can do certification in the black box setting. But my talk is mainly focused on attacking in the black box setting. So I found the attacking a little bit hard in the black box setting when we don't have any access to model parameters. So I think the certification would be probably even like a lot harder based on just my intuition. But just this talk is, I think, addresses an easier problem, if I can say. It's just the problem of attacking with reinforcement learning. And I'm attacking, we are attacking in this talk, we're targeting malware detectors specifically. So here is a little bit of background. This is me on the right. I just graduated last week from University of Arizona, and I'll be an assistant professor at University of South Florida in August, hopefully. And yeah, my master's is in computer science, my PhD is in information systems, and a research interest is in AI-enabled security and statistical machine learning. And the work I'm going to present to you guys today is a joint work with Jason Pacheco, Weifeng Li, James Hu, and my advisor, Dr. Chen. So, okay, let's, without further ado, just jump into today's talk. So we know that AI facilitates cybersecurity, and to the extent that 69% of organizations believe they cannot respond to cybersecurity threats without AI, based on a survey that was done recently. And also, on the other hand, 90% of US cybersecurity professionals expect attackers to use AI. So I think that's what we mean, like by security of AI is becoming very important. So that's the overarching reason for this research. The main motivation is what I just described, and we know that, however, these AI agents have shown to be vulnerable to adversarial attacks. And these are the inputs that are meticulously modified to mislead these AI agents. And let's just call them adversarial attacks, as we saw. So this is just an example in the self-driving cars, because to me it was easier to grasp it the first time when I was learning about adversarial attacks. And in the image it was easier, and we saw in the previous talk as well how we can create these perturbations. So we form an adversarial input attack that is detected as completely something different. So a stop sign will be detected as a speed limit 45. So the results are devastating, the result of this attack. So what I'm going to do today is just focus on conducting these attacks for basically malware detector against malware detectors. And I think we need to kind of remember that even though this is kind of a malicious tool when it's in hands of hackers, being able to simulate adversarial attacks on the side of defender is actually beneficial, because with having those attacks, we can learn how to robustify our model against those attacks. So yeah, it cost the economy a lot, these kind of cyber malware attacks. And we know that these the malware detectors are the first line of defense, and it's not a good thing if they're vulnerable to these attacks. So that's probably the main that's basically the main idea of, or main motivation behind our research, to be able to simulate these malicious attacks or samples. So if you see in the figure, we have this original malware, which is already detectable by the malware detector, and then we modify it with some perturbations, and then in a way that it becomes undetected. So that's the overarching goal. So I'm going to call it adversarial malware example generation, or AMG for short. And as I already mentioned, even though bad guys can use it, if we can simulate AMG, we can bolster the resistance or resilience of our model. How we do that is not the main that focus of this talk, but I think generating high quality evasive adversarial attack is mostly the main focus of this talk, which is, I guess, maybe the 50% of the focuses on the 50% of the solution. So if we look at the recent studies in the last maybe 2 to 3 years, we see that the one that so these are basically the black box ones, meaning that they do not require access to model parameters. And we have another more restricted version called BBB, like triple Bs. That stands for a binary black box. And that means not only you don't have access to model parameters, but also the only output that you can see from the attack target, which is in this case our malware detector, is just a binary response. It passed or it didn't. So you don't even get a real valued response, which sometimes we call it a confidence score of the model, like let's say 60% this wasn't malware and 40% it was benign. So it's just 0 and 1 just to make it more realistic. And then we can see that most methods rely on additive adversaries. Additive versus editing usually means for additive, they just inject some perturbations to the malware binary without editing any parts of the malware. So we think that changing or flipping parts in the binary results in more powerful adversarial attacks. And also, most methods do not account for modeling the adversary's actions. And what we see is there are two, the one that I highlighted with yes. These are the one that use deep reinforcement learning, and they can keep track of adversary's actions, as I will show at the end of this talk, how we do that. So just a brief overview of reinforcement learning. So it's basically a Markov decision process, and given a state S, the agent takes an action A, and in response, the environment, as seen in the little figure here, the environment produces a reward R, which could be defined as a function of state and current state and current action. And the goal is basically learning a policy that maximizes the reward of the RL agent. Well, definitely we are talking about the reward in expectation. and this capital R is basically accumulated reward, like from the beginning of the episode till the end. And so learning the behavior and adversary if we model things with reinforcement learning is going to be translated to learning a policy, as I just alluded to. This policy in deep reinforcement learning is could be kind of approximated with a simple neural network, and that's what I basically mean by deep reinforcement learning. And the model, one of the most breakthrough models in deep reinforcement learning is called AC, or actor-critic model. And then in 2019, they came up with another variation of actor-critic model called VAC, and which just uses variational inference to enhance classic actor-critic model. But I think still the model works a lot like actor-critic. And in actor-critic, we have two steps, basically two iterative steps. One is policy improvement, one is policy evaluation, and these two are kind of closely related to expectation maximization, if you want to think about it. And then the actor finds a policy pi that is compatible with the current action value function Q, and that the policy evaluation phase, the critic estimates the action value based on the current policy that was kind of guessed with from the previous steps. And then both of them can be modeled as neural network. But the thing is that in classic variational actor-critic model and also actor-critic model, the output of the policy network is usually a continuous distribution. So we sample from that continuous distribution to take actions and apply them to the environment. And
we have
this
one
is
more minute if we can. Sorry, wrap up because we're
okay. Sure.
schedule. Sorry for that.
No problem. I'll try to speed up. So with that model preliminary, then we have the threat model here that we're going to try to implement. The adversary's goal is to automatically generate malware variants that evade the malware detector. The capability is that we want to create functionality preserving malware that
Sorry, Nick.
Yeah.
I think we actually have 10 minutes more.
Do we started at 3:30, well, 1:38.
Yeah, we have an hour and a half for 3 talks, which is 30 minutes a talk.
Oh, sorry, I completely, sorry, my fault. My fault.
You still,
Okay,
you still
keep
have
going.
10 minutes left.
Yeah.
Okay, 10 minutes is great because I was scheduled for 25 minutes actually, and I think I can
completely,
be.
yes.
Thank you.
Yes.
Yeah, thank you for that, Dr. Carlini, and thank you, Dr. Bosio. Okay, so this is the threat model. The capability of the model, the adversary's capability is to applying allowable, which means functionality preserving actions. And then the knowledge, which is the most important part, is that we don't know the parameters and deep learning architecture of the malware detector, so it's completely black box, and we don't have any access to the real valued confidence that I described in the beginning of the talk. And the only available information is just that binary output. Is it passed? Is it evading or not? So this threat model gives rise to this action space that you see here. There are 2 types in this. I don't know if you can see my mouse cursor as well. I hope you can. Oh, that's awesome. Thank you. So then this action type is additive or editing. I think we have 5 additive and 5 editing action, and we based it on a work done by Anderson et al., and we expanded on those. And then things such as removing the signature of files, change the timestamp of file, and so on. So some of them are editing, some of them are editing, and this is where, like, we can call it the attack surface, where it affects the the executable file, in what section of the executable file. So the executable has headers, sections, and an overlay append, and then these actions are affecting these parts of this executable. Okay, so the main problem that we have usually to directly apply a VAC is that the actor network in VAC has a continuous policy, actually. And when we want to apply it in such a discrete action space, it's not that easy because the action space is basically discrete. And the main reason when I say it's not that easy is that this stochastic gradient descent that we rely on for the actor network to train the actor network is going to be hampered if it's not if we don't use a continuous space, if you're not sampling from a continuous space. So Madison et al. Has showed that discrete samples can be approximated via using a differentiable distribution called concrete distribution. So that's basically the main idea that we want to use, and inspired by them, we want to approximate this discrete action distribution over these attack vectors that I just have here with this. And this is just, again, what concrete distribution does, which probably in the interest of time, I'm not going to get into the detail, but it has two main steps. First, we sample IID random variables from a distribution called Gumbel distribution. And then the second step, so that's the very, this part, that's the Gumbel distribution IID. And then this is the output from the policy network. So this is discrete. But when we combine it with component-wise addition with this Gumbel distribution and apply a softmax layer on it, well, there's theoretical guarantees that then we can sample the discrete distribution as if it was a continuous distribution. So that's basically the trick that we use to just make this happen. And if we compare the normal VAC with the AMG VAC here, the one that we propose, we can see the only difference is in here. Like this is on the left is the classic one, and then on the right is the tweak that we make to AMG VAC to make it work on work with approximate sampling. So apply this technique to the output, and as you see in this kind of schematic figure that I put here, the approximated concrete distribution is the orange one here, and it's built on top of these discrete ones, and these discrete ones are the actions that you have seen already. So that's basically the big picture of what we try to do, and then let's apply it to see how it works in action. So we have a testbed of 3 gigabytes of to train these 3.2 gigabytes for training, and then we applied on a 30 gigabyte evaluation set so far. And then the training set have adware, botnet, and ransomware, and it has 6 main categories of malware. And so when we want to apply it to malware attacks, this is how we define this action. We have state, we have actions, and we have policy, and the action sequence, which I'm going to show you later. And the reward that we defined was 10 for each of them based on Anderson et al. So we just followed strictly their design actually here. So nothing new here. And then for the evaluation overview, so we're gonna apply the attack against these malware detectors. I think in this work I'm going to talk about Light GBM and Malconf, as we'll see. So these two I'm going to evaluate against. And then so for the benchmark methods, one is this benign feature append that we have. It is a black box append attack, and it's basically not binary, but it has a little bit of advantage against our method. But but we'll see that we can still the method can still outperform it. And then double deep Q learning, and also a version of actor critic with experience replay, or ACER. These two are binary black box. So we compare against both of them, and the ACER is the one that was used in Anderson et al. 2018 as well. So I think it was one of the, I think maybe the state of the art, that I don't think probably it has the most the best performance. And so we compare against all these three, and when we see that in the benchmark evaluation, and we build the class, we evaluate it separately for each of them, for each malware type, adware, botnet, and we see that without any exception, on average, on all of these six, we see that when we just apply the technique that I just described, we get 37% more evasiveness without damaging the false positive. And I think that's just achieving this evasion rate, I think, is interesting. So I think it could be considered as a strong attack. It's a little bit subjective, but maybe compared to other methods, it's a strong attacks. Benchmark methods that we have is a strong attack. But the nice thing about it, applying this technique, is that we can analyze these action sequences that I just talked about. So, for example, on the right here, you can see what the adversary has done, the simulated adversary has done to build an evasive sample. And what we see is that for the Ember, which is a feature based on feature vector, and Malcolm uses the whole binary, and it's a CNN basically on the whole malware binary. Ember uses feature vectors. So we see that on Ember, most of the actions that leads to evasion are basically editing action, and here the situation is the same in the Malcolms. We see that 39% of them are is an editing action, which is this is a compression action. And then, so the compression affected both of them. And then, so we can kind of get this kind of observations with analyzing the sequence. So three things from this sequence is that compression affected both malware detectors. And then the ML-based Ember, which works based on light GBM algorithm, was more sensitive to editing actions, while on the contrary, the DL-based Malcolm was more sensitive to additive actions, which means appending and injecting bytes into it. But Ember is not that easy to fool with additive actions. So these kind of characteristics of these is going to come out. So I'm not going to get into more analyzing these, so we can go deeper and analyze it for each category as well. But one thing I want to say is that we see that compression often appeared as the last action in the sequence. So, and also some actions such as section rename was often used due to its applicability to different sections, because they can be applied to any section of a malware binary. And I think these two kind of patterns that we have kind of aligns with a human hacker, probably with what they would do, maybe align with those, which means apply the changes first and then obfuscate the code last, which is to compress everything last to make it evade the anti-malware. Yeah, I'm not going to get into more analysis of that in the interest of time. And then, but we can do all types of, it's kind of, this reinforcement learning thing, I think, gets us this ability to interpret the result in a nice way, and use it to make more robust models. And yeah, so maybe just one future direction, if I want to point to, is that I think the future direction, at least for me, is, especially motivated by the talk that I listened to from Dr. Vechev in the beginning, is try to do the second half of the target, the second 50% of the story, which is, okay, now we have realistic adversarial attacks, how we can enhance the robustness of these DL-based malware detectors against adversarial attacks. So that's just what I wanted to share with you guys and know your feedback today. And thanks for listening. And I would be happy to answer any questions if there is one.
Thank you very much, Mohammadreza, and I apologize for stressing you. I just miscalculated the time.
That's totally fine.
That's
totally fine.
Yeah, we owe you 3 or 4 more minutes. I don't know. I'm trying to see on the Q&A if we have any question. I haven't seen anything so far. So I don't know if Nicolas or Lorenzo, you have any question. I wanted to let's wait a little bit to see if there's any.
No problem.
Sure, I'll ask a question.
Mm-hmm.
So, were you able to listen to Sadia's talk in the morning?
No, I missed that one, unfortunately.
Okay.
Yeah.
Okay, so I guess I don't want to maybe put too many words in Sadia's mouth, but she talked about sort of what attacks, when attacks matter because like they're in feature space versus in like the actual real domain. Maybe okay. If you didn't see her talk, maybe my question won't make too much sense. But I guess I would encourage you to listen to Sadia's talk because I think it's very related to what you were doing.
I will. Yeah, it's recorded, right?
Yeah, we tried to record this.
That would be great. Yeah, I really scheduled to do this, but tomorrow is actually my wedding, so
I
was just
congratulations.
Thank you very much. So I was just running, doing things.
That's exciting.
Yeah, thank you very much. But I'll definitely listen to Sadia's talk
after
your wedding.
Yes. Otherwise, my wife is going to be very unhappy with me. So
I would say way after your wedding. So.
Sure. Thank you, guys. I'll definitely listen to that. And yeah, that's pretty much. Oh, I see a lot of congratulations. Thank you, guys. I'm glad that I brought it up.
Okay, well, I guess maybe we'll move on to the next talk then.
Yes, let's move to the next talk because we're a little bit behind schedule. Thank you again.
Thank you.
So I think we have Jiayi here. You can share your screen if you want. So we're going back to the first talk. MMGuard, automatically protecting on-device deep learning models in Android apps. Welcome, Jiayi from Beijing University of Post and Telecommunications. Can you try sharing your screen?
Yes, I'm trying to share the screen now. Can you see my screen?
We're good to go, yes.
Okay. Hi, everyone. I'm Jiayi. I'm from Beijing University of Posts and Telecommunications. I'm going to talk about our paper, MMGuard, automatically protecting on-device deep learning models in Android apps. Smartphones are one of the key drivers that push forward the future of artificial intelligence. On-device deep learning models are gaining great popularity in mobile apps, which offer benefits desirable for both model users and app developers. App developers are relieved from the expense of maintaining code service or server, and app users don't need to concern about the privacy issue and the network latency. But on-device models inevitably introduce new challenges, new security challenges, like model stealing and model tampering. Model stealing means the attacker seeks to steal the target model and deploys it in his own apps or services. Training a DL model often requires lots of resources, including proprietary training data, algorithm, and computational infrastructure. If the DL model is unprotected in the app, an attacker who has basic reverse engineering ability can easily extract it without much effort and reuse it in his own mobile apps. But according previous work, nearly half of the studied apps didn't adopt any model protection. This will definitely infringe the intellectual property of model owners. Model tampering means the attacker intends to tamper the original model to achieve some malicious purposes. DLs have been found vulnerable to various kinds of attacks, like backdoor attack, adversarial attack. For example, the attacker may modify a face recognition model, try to make it recognize him as the one with privilege, so that he can pass the access control system. Since most of the on-device models are lacking of protection, and no systematic tools can be easily used to protect the model effectively, it is important and urgent to have a proper protection mechanism for such on-device models. Existing work had proposed mainly two types of methods for model ownership protection. The first type of method embeds model owner's signature into weights by training model with additional regularization terms. For example, researchers can embed the secret bit vector directly into the size, least significant bit, or some statistical information of the network parameters. The second one is training model using adversarial samples and specific labels. The owner's signature can be represented by the input sample and its unique predicted result. For example, the owner can synthesize a trigger set by selecting a set of images based on the signature. For each image, selecting a target label, then poisons the training data set with the trigger set. Finally, trains the model on the poisoned training set using a standard training pipeline. However, these methods have some limitations. First, almost all these methods need to be applied during training or fine-tuning phase, therefore are inapplicable for a released app as its model's parameters are frozen and training metadata is unknown. And these methods may sacrifice the accuracy of the model. Second, some methods cannot prevent the model from being stolen, but only can help to prove ownership of the model after suffering losses. Moreover, it has been proved that some methods are not robust enough. The detection accuracy of signatures embedded in DL models can be greatly reduced, or it is possible to forge counterfeit signatures. So we built MMGuard to protect the deep learning models in mobile apps, and we want to address these problems. Here are some background information of MMGuard. We do not require model retraining or any prior knowledge of training data. We make this assumption because we consider app core developers who have no access to the training data and reinforcement service providers and app store regulators as potential users. We consider the attacker have a number of abilities to hack the app. Firstly, static reverse engineering ability. The attacker can decompile an APK package and access to app assets where on-device model is stored usually. Second, app packaging ability. the attacker can modify the on-device model, like inserting a backdoor and repackaging the APK with the original model replaced. Then the modified APK file is signed by attacker's own signature and released to app markets. Thirdly, basic dynamic analysis ability, which is a higher level ability. The attacker can instrument candidate API like load model to dynamically find the memory buffers of DL model. And we summarize 7 requirements of an intended DL model protection approach, including fidelity, integrity, confidentiality, and so on. MMGuard consists of 2 procedures, model protection and runtime verification. The key idea is taking signature-related information as an extra input to the model. Let performance of the packed DL model drop dramatically when getting a wrong signature as input. In the model protection phase, for a given app, MMGuard unpacks the app, extracts code and the model from it. Model developer chooses a developer-specified token, a message that only he knows for his app, as the evidence to prove his ownership, and 1 or more convolutional layers from his model where the weights are valuable. MMGuard generates key app based on the token. Then for each selected convolutional layer, MMGuard modifies the logic of model with key app, recompile the model with code verification, and computes the hash value of recompiled model. Next, MMGuard replaces the original machine learning library, like TensorFlow, in the app code with a modified one that contains additional model verification logic. Finally, the output is a new app with protected code and model. The modification of the logic of model is shown here. The picture shows the structure of 1 convolutional layer before and after modification. First, MMGuard creates the signature as app by hashing the developer-specified token. Then uses pseudo-random number generator with seed as app to generate key app. The length of key app depends on the size of weights of selected convolutional layer. As app and layer number are indispensable in our protection approach. Second, MMGuard subtracts key app from the weights, saving the results as new weights. Finally, MMGuard adds an input branch and tensor addition operator in order to recover correct weights during running procedure later. MMGuard combines the signature as app, hash value of modified model, and the selected layer number into an input info file, which is stored within the app, but can further be stored in security memory like trust-zone or remote server. At runtime, when mobile user triggers the DN functionality at the first time, the app will initialize the inference interface. During the initialization, the deep learning framework extracts input info file and reads the hash value, computes a hash of existing model. If these 2 hash values are matched, the app continues to read as app and selected layer number from input info file. Otherwise, it will abort initialization. Every time the app runs the model, it gets original input and feeds to the model. Then for each selected convolutional layer, the app feeds key app to the input branch, where key app is calculated by a pseudo-random number generator using as app as seed. Thus, the weights are recovered. The performance of modified model will be significantly deteriorated if as app is wrong. Our evaluation is driven by these two research questions. Can MMGuard protect the mobile apps from being hacked by both model stealing and model tampering attacks? And whether MMGuard fulfills the requirements mentioned before. To answer question 1, we perform a qualitative analysis and take an image classification app as example. We compare the app in different scenarios, including normal, model stealing, and model tampering. The first picture shows the normal results of the app, where the app classifies an image of table and chairs as dining table and rocking chair. If an attacker intends to steal the model and deploy it in his own app, he may decompile the app and extract the model file directly by static reverse engineering, or instrument the API like load model to dump memory buffer where the model is stored, which will cause model encryption invalid, for the model is completely decrypted at runtime. However, in our approach, the weights of stored or loaded model have been modified. Even if the attacker can successfully run the model in his own app, the model cannot work as expected. As shown in this picture, the image is misclassified as a purse. If the attacker tries to tamper the original model and repackage the APK with the original one replaced, the result is shown here. Any small alterations in model will lead to the failure of runtime verification. Thus, the execution will be terminated, leading to no classification results provided. We next devise experiment to evaluate whether MMGuard fulfills the approach, the proposed key requirements. MMGuard is implemented based on TensorFlow 2. We build a demo Android app and measures the performance of MMGuard on 5 popular neural network models, such as Inception, ModelNet, and so on. We measure the overhead of model usage on an Android 7 device. And to evaluate the scalability of MMGuard, we crawled over 10,000 popular apps from Google Play and collected 43 apps that have on-device model for the experiment. The first requirement is fidelity, which means the modification of the model shall not affect its functionality. We manually investigated the 5 models in the demo app we created and found that all these models behave the same as the original models after performing protection, because we will generate a same key app based on the feature of pseudo-random number generator at runtime. The weights used to inference are same. Integrity requires that the prediction results of model before and after modification for an input shall be equal only if the model app have correct key app generating from correct signature. The demo app can generate correct key app and recover the correct weights only when taking the right signature at the input. Any difference in signature will lead to a different key app, affecting the accuracy of model. Confidentiality means it is very hard to get the entire model based on model inputs, modified model, and prediction results. This can be fulfilled because it's very hard to calculate key app without the help of signature as app. Also, it will take some efforts to guess which layers are modified. The efficiency of MMGuard is measured by considering both the initialization overhead and the runtime protection overhead. We run 50 times for each type of model, and the average time is reported in the table. At initialization time, the overhead is introduced mainly due to the increase of model size and the computation of hash value. Overall, the overhead is around 449 milliseconds on average, which we think is tolerable because it is a one-time overhead. At routing stage, the overhead is mainly brought by calculating of key app and the extra input feeding. The overhead is negligible, with a maximum of 16 milliseconds. To evaluate the scalability, we apply a MMGuard to protect the models in the 43 apps from Google Play. Overall, 37 of them, which is nearly 90%, can be protected successfully by MMGuard without providing any additional information. The failures are mainly because of unsupported model type and unsupported operator type. In real-world usage scenarios, app developers can use MMGuard to automate the model protection on their released apps conveniently. For capacity, the model owner defines a secret token, and the hash of the token is the seed to a pseudo-random number generator. There is no limit to owner-defined token, but only a limit to the length of signature in implementation. Nevertheless, it is enough to claim ownership uniquely. The cost of cracking the signature is super high. Irremovability means the attacker cannot escape or eliminate the protection mechanism easily. In the approach to escape or eliminate the protection mechanism, an attacker might try to remove input branch from modified model in order not to feed any key app. Although the attacker can succeed, the accuracy of model will be quite low. The attacker still need to get the correct signature. Therefore, a MMGuard can meet the above-mentioned requirements. In general, we propose a MMGuard to protect the on-device DNA models by adding extra input branches, which take in owner-related signature information as input. We should admit that the implementation of MMGuard carries several limitations. MMGuard inherits some compatibility issues. For example, we only choose convolutional layer as the protected target. We only consider TensorFlow now, and we cannot deal with custom operators. And we can address these limitations by expanding our method to more types of DL tasks and supporting more kinds of versions of DL frameworks in the future. MMGuard cannot prevent GPU-level theft like Hermes attack. Also, if the protection mechanism of MMGuard is known to a sophisticated attacker, or the input information is exposed, he may try to change the code logic in DL framework or manipulate the input information to break our protection. However, MMGuard can increase the effort to attack an DL app greatly, which can protect the model from being easily hacked. We can turn the problem of protecting a large model file into the problem of protecting a small input information. Unlike other existing methods, which may be time-consuming and do harm to model accuracy, our approach does not require model training or any knowledge of training data. Experiment results show that MMGuard is both available for apps under developing and already released with negligible impact on user experience. More advanced methods like Trust Zone can be further adopted with MMGuard to provide stronger protection. Thank you for your attention.
You're welcome. Hi. We do have one question from Jacob Bond. As how does the app hold onto the secret developer token in a secure way? I'm not sure. Do you see the question?
Oh, I'm seeing the question now.
It's in the Q&A. I'm just reading it again. How does the app hold onto the secret developer token in a secure way?
No, this the secret developer token will be hashed and as C app and S app and stored in the input info file. This file is now stored in within the app, but the developer can change the problem of protect the whole model, which is very big now, and into the question to protect the smaller input info file. And if this file is not found by the attacker, and the attacker cannot know the secret developer token, and and the attacker cannot break this protection approach. And
I see.
this input info file actually can further stored in trust zone or some remote server. So this attacker cannot manipulate the information in this file.
Okay, so there's actually a follow-up if I want to ask something. So rather than having to say encrypt a large model, they just need to say encrypt the smaller info file. Is that what you're saying? I think.
Yes, this what the developer can do to protect their model.
I see, and you also mentioned that you're limiting your model into convolutional neural networks. Okay, is that right? You consider that something that I didn't get. Are you protecting models that they have to do with convolutional neural networks, or it was your technique using it? So you mentioned that as a clarification was in your last slide. You said that there's a limitation because you're only dealing with convolutional neural networks.
This is because we just try our implement our method on convolutional layer. Actually, this doesn't matter which kind of model
the user, okay,
the mechanism, because the models have if the models have some valuable weights, we can easily transfer this method to different DL tasks.
Okay, thanks. I think it's pretty clear. We don't have any other question. I don't know if I actually request the next speaker to make sure that he has access to the screen, to the video. That's Limin. I think Limin Yang. You see on the pause. Okay, so we get a request. Okay, we get a request. Okay, it's in. I don't know if I don't see any other question. We're actually right on time. It's thank you very much, yeah, for the talk. Okay, I think we did the perfect permutation. Nobody actually got the original time slot in this session. So we have Limin Yang from the University of Illinois at Urbana-Champaign, and he's going to talk about BODMAS, an open data set for learning-based temporal analysis of PE malware. Can you try to share your screen? And we can see. You're good.
Okay.
You're good to go.
Okay, sure. Thank you. Thank you for the introduction. Hello, everyone. My name is Limin Yang. I'm from UC, and I'm a PhD student there. Today I'm going to talk about BODMAS, an open dataset for learning-based temporal analysis of PE malware. This is a joint work with collaborators from Blue Hexagon and my advisor, Professor Gang Wang. To begin with, why we need an open malware dataset? It can help new research to solve new problems. And with benchmark datasets, we can easily keep track of the state-of-the-art methods. For example, the top figure here is from the machine learning community. It shows the top 1 accuracy trained with different self-supervised learning methods on the ImageNet dataset. This is a great figure. It can help us to track researchers' progress on the same dataset. When can our security community plot a figure like this? As we all know, security community lacks benchmark datasets. Unlike the image domain, they have classical datasets such as MNIST, CIFAR10, and ImageNet. So what is preventing us from sharing a malware dataset? There are several challenges compared to other domains. First, legal restrictions. We cannot share benign binaries because they are often protected by copyright laws. Another problem is the labeling costs. Usually, unlike other domains, labeling a PE file is benign or malicious is very time-consuming, even for well-trained experts. Also, we cannot share anti-malware scanner results because they might be proprietary. And another problem is we are taking some risk to share malware to non-InfoSec people because the malware could accidentally execute on their computers. And lastly, since malware evolves and a new malware family appears, we need new malware datasets constantly to keep up with the trend of the attack. To resolve these challenges, we tried our best to release a new PE malware dataset. For the legal restrictions, we released feature vectors of malware and benign, and we share malware binaries only. And to have curated labels, we have in-house tools to analyze and aggregate multiple antivirus vendors' labels. Besides, about 1% of the samples were labeled through manual analysis. To protect the audience, we only share disarmed malware with the researchers upon request. And lastly, we released a more recent dataset sampled from a security company, Blue Hexagon. Let's take a look at existing public PE malware datasets and how our dataset is different. Here we find 4 existing datasets from Microsoft using Santa Barbara, Amber, and Server 20 million from Sophos. The first problem is these existing datasets are slightly outdated. Microsoft does not have timestamp information and is before 2015. The middle 3 are mostly from 2017 to early 2019, while our dataset BODMAS, it covers about 1 year data from middle 2019 to 2020. Another problem is most existing datasets do not have curated family information. Microsoft only has 9 families. UCSB and Sora do not provide family information. Half of Amber indeed provide family labels, but after closer inspection, we believe some labels are not the real name of a malware family. In comparison, our dataset BODMAS has curated family information with more than 500 malware families. Also, we keep the same format for the feature vectors as Amber and Sora. This gives us the luxury of combining them together to have a 3-year longitudinal analysis. We just briefly introduced our dataset. Now let's see what can we do with this dataset. Thanks to the temporal information, we did some preliminary analysis on an open problem called concept drift. We will first discuss the concept drift in a binary classification setting. Let's take a look at a quick example for a binary malware classification model. In the training phase, you have benign and malware, and you train a classifier. And during the testing time, if the sample is benign, you classify it as benign. You can classify it as malware. However, what if malware evolves and pretends to look like similar as benign? Attackers always try their best to update malware and avoid detection. In this case, the classifier is likely to classify it as benign, which is wrong. This is where concept drift happens. This malware is one type of drift called in-class evolution. On the contrary, benign binary could also evolve and unintentionally to look similar as malware. In this case, the classifier is also likely to classify it as malware, which is also wrong. Concept drift happens again, and this benign binary is also in-class evolution. To evaluate the concept drift in the binary classification over time, we did an experiment using available malware datasets. Here's a timeline from 2017 to 2020. Recall that Amber dataset is from 2017 to 2018. We split it as 80-20 training and validation set. And we train a gradient boosted decision tree model. We train it 5 times with 5 random seeds. Then during the testing time, we split our BODMAS dataset to 12 testing months, namely 12 testing sets, and feed to this gradient boosted decision tree model to get a prediction. Similarly, we have the UCSB dataset as a training and validation set. We train a GBDT model and evaluate on the 12 testing months of BODMAS dataset. It's slightly different when using Sora 20 million as the training and validation set. This dataset is big, and due to resource constraints, we use the pre-trained GBDT model and deep neural network model and evaluate on the 12 testing months of the BODMAS dataset. Now we're clear about the experiment setup. Let's see how is the result when using different datasets as training. We mainly care about the false positive rate and the F1 score. In the validation phase, we control the false positive rate to be no greater than 0.1% to simulate a more realistic setting. We can see most classifiers got more than 98% F1 score. During the testing time, we have 12 testing months sets for each month. For Amber, mostly false positive rate is no greater than 0.1%, but F1 score dropped in some months, especially the last 2 months, only 92. For the UCSB, the result is not surprising. It shows the largest drop because it's a specialized dataset, contains mostly packed and obfuscated malware. Thus, it may not generalize well to our dataset. For Sora GBDT and Sora DNN, we experienced some large false positive rate in a few months. It's potentially caused by the drift of benign samples. Sora GBDT mostly have good F1 score, but still dropped in some months. Sora DNN performs worse. It's possible it can perform better with further fine-tuning, but due to resource constraints, we use the pre-trained model and didn't fine-tune. To conclude the impact of concept drift in this setting, most classifiers got 98% F1 score on validation, but degraded, sometimes even a lot, on our dataset BODMAS. Also, a more important finding, concept drift could be discrete events instead of a monotonic trend over time. We can see some months have a larger F1 score drop, but some months are doing okay. So to mitigate this concept drift, we tested 2 methods. The first one is called incremental retraining. We use Amber as a baseline and adding 1% samples from the second month of BODMAS to the training set. We retrain it and test it on we add 1% samples from the first month of the BODMAS dataset to the AMBER training set, and we retrain the classifier and test it on the second month. Then we cumulatively adding this 1% samples to the training set from the second month of the BODMAS, and we retrain it and test it on the third month. Repeat this process for the rest of the months. Did this work? The x-axis is the testing months representing each testing set. The y-axis is the F1 score. The blue line is the results using AMBER as a baseline, and other 3 lines are from incremental retraining. We tried 3 sampling strategies when we select the 1% samples. Non-conformity is adapted from a paper from Lorenzo called Transcend, means how much an input sample does not fit into existing classes. Thank you for sharing the code with us, Lorenzo. Probability is probability produced by the classifier. Random means we just random pick 1%. And we can see by labeling 1 sample per month, all the F1 scores surpass 97%. And the different sampling methods have close performance. Non-conformity is slightly better than random. Another strategy is forget about the existing old data sets. We take 1 month, the first month from the BODMAS as the training and validation set. We train a new classifier with this 1 month new data and evaluate on the rest of the months of BODMAS. As the result shows, the blue line is still the AMBER baseline, and the red line is the result from training with 1 month new data. We can see that labeling new data and training a new classifier indeed improves the F1 score. But still, a slight downward trend still exists, indicating the impact of concept drift is still there. We further analyzed the reasons of false negatives when using 1 month of BODMAS as the training set to train a new classifier. Thanks to the accurate malware family information, we can attribute the reasons to 2 categories. The first one is existing families, means that the misclassified samples is from an existing family of the 1 month training set. And another one is from previously unseen families, means the misclassified malware belongs to a family that never appears in the training set. As we can see, the right column, unseen family, is usually much bigger than the left column, existing family. From the table, we know that existing families indeed produce some false negatives. For example, they might be from malware variants. Also, unsurprisingly, unseen families are more likely to be misclassified as benign than existing families. Now we have some sense of what is concept drift and how it affected the binary classifier over time. The next question is, how about the concept drift in a multi-class classification, namely malware family attribution? Here we use a similar example to illustrate a multi-class malware classification model. In the training phase, you have benign malware family A and B, and you train the classifier. Then during the testing time, it should be from one of these 3 classes. But what if you got a malware C that you never seen in the training time? Clearly, assigning them as benign, malware A or B, they are all wrong. This is where concept drift happens. Malware C is another type of drift called unseen family. This quick example reminds us two settings for malware family attribution. One is called closed word and another is open word. In the closed word setting, we assume both training and testing sets will contain samples from all N families. However, the open word setting proposes a more challenging problem, yet more realistic. In the open word setting, the number of families N could be large and increases over time. Also, we may have malware from previously unseen families, like malware C I just mentioned. According to FireEye report last year, they analyzed 1.1 million malware samples every day and about 41% malware families were never seen before. This is definitely a serious open challenge. To evaluate the concept drift in the malware family attribution, we did an experiment using our BODMAS dataset. Other datasets do not contain enough curated family information, that's omitted here. We take top N families from about 1 month of BODMAS as a training set and train an N families malware multi-class classification model with malware only. Then during the testing time, we evaluate the model and the rest of the 12 testing months from BODMAS. Here is the result for the accuracy on the testing set. The axis here is still each testing month, and the y-axis is top 2 accuracy. We also have top 1 and top 3 accuracy in the paper. Top 2 accuracy here is similar as an image domain. It refers to the likelihood that top 2 predicted families contain a sample's real family. For example, if a malware is from family A, and the top 2 predicted families are B and A, then we count it as a correct prediction. But if it's predicted as malware family C and B, then we think it's a wrong prediction. The green line here shows the number of training families n equals to 10. And known means testing set only contains sample from these 10 training families that we already knew. We can see the accuracy is pretty good, always more than 95%. Remember, this is a closed world setting. But what if we change it to an open world setting? We end up with the orange line. Or means that we use all the testing samples, including those families that we never seen in the training time. We can see a sharp drop in terms of top 2 accuracy. Now the accuracy is only about 20% to 60%. The errors are largely attributed by those unseen families from each testing month. So how about the performance when we increase the number of training families? For example, we increase n equal to 40. When the testing sample, we only consider known families. Compared to n equals to 10, we can see a clear drop in terms of the accuracy. This indicates that a larger number of families is harder to train. When it turns into all testing samples for n equals to 40, as expected, it's not as good as the purple line, n equals to 40 with known families only. And people may wonder why it's better than the origin line, n equals to 10 with all testing samples. This is because with a larger n means we have fewer unseen families during testing. Thus, the accuracy is better than n equals to 10 with this origin line. We further study n equals to 80, the brown line here at the top. It might seem strange that y is close to the n equals to 40 with known families. It's because when we further increase n, the later families do not have many samples, thus have minor different influence on the overall accuracy. For example, the top 50 family may only have few samples. And similarly, when we consider all the testing samples for n equals to 80, it's worse than the n equals to 80 with known families, but it's better than the n equals to 40 because we have fewer unseen families during testing time. After seeing these figures, now we have the following conclusions. Previously unseen families indeed significantly degraded the performance of our classifier trained in a closed world setting. Also, it's harder to train a good classifier when the number of training families increase. For example, when we increase n from 10 to 40. After the preliminary experiment on the BODMAS dataset, we spot some open challenges. To mitigate the concept drift of malware evolution and unseen family, we need out-of-distribution detection. And also it remains a challenge to scale to a large number of malware families and to explore the relationships among them. And lastly, we need to combat against the real-world adversarial samples of malware binaries, just as Lorenzo's Oakland paper discussed. To conclude, release a new PE malware dataset with timestamp and malware families. And also, concept drift poses a challenge for both malware detection and attribution. And lastly, unseen families are more likely to be misclassified than known families. Thank you for listening to my talk. Feature vectors and metadata are open to public. And if you need malware binaries, shoot us an email. Also, check out our upcoming user security paper. And now I'm happy to take any questions.
Thank you very much, Limin.
Yeah, thank you.
I think it's a very interesting data set. I just want to ask the first question: if you've already had any applications or any papers already? I mean, I believe you've already published that. What kind of interest have you seen so far?
Yeah, we actually have a paper in using security paper that partially use this data set to evaluate the concept drift detection. And also we propose an explanation method to explain those drifting samples.
At what time scale does this drift happen? Like, is there one of the angles that you are analyzing?
Sorry, I didn't hear clearly.
So we're talking about drift. Are you talking about like distribution drift or concept drift over time? Is that an angle that you're taking?
Yeah, actually, this paper is more focused on the multi-class classification model, and we also have a preliminary analysis on the binary classification. So it's more like using the KID to detect out of distribution, to detect out of distribution in the multi-class classification setting.
I see. Let me see if there's any question on the post chat. Yes, I don't see anything. We're heading towards the end of the session. I don't know if Nicolas or Lorenzo have any other. And you said this is the 2021 that's upcoming, yes? Okay.
Yeah, it will be shown in August.
Yeah, I guess I would just ask, like, what do you think is the next, like, most useful thing you can imagine to do with your data here?
I think it's very interesting to. First, we only did a preliminary analysis on the concept drift, and I think with this dataset, I'm more interested on the explanation method. For example, currently we only have the, like, feature-based explanation, and I'm more interested on like taking the behavior-based of those malware to, for example, to develop an explanation method to provide explanation for why this sample is a malware because of some behaviors showed. I think that's a quite interesting angle.
Could you expand on what you mean by feature versus behavior?
Oh, the feature is just, for example, the feature is extracted from some static analysis. It originally may not seem meaningful. For example, the histogram of bytes, the binary bytes, it does not have meaning when you present this feature to a human analyst. It refers to the behavior. For example, it downloads malware, or it lures you to open a phishing website. That kind of malware, kind of behavior.
Okay, I see a question. Sorry, do you want to?
Oh, okay.
No, please ask a question. Yes.
Yeah, so there is like nice presentation. Have you found any specific kind of concept drift, like sudden, gradual, incremental result in recurring drift?
Thank you. I think we didn't explore the category of concept drift because we don't have the ground truth. For example, which sample is evolution. We do have ground truth when a sample is from unseen family. I think this question is more likely from the machine learning angle, but from the security angle, we probably don't have the ground truth for this kind of categorization. I'm not sure if that answers your question.
Let's see if there's any response.
Yeah, thank you.
Yeah, okay, so thank you. I don't see.
I have maybe like a very quick question, Limin.
Yeah, sure.
Perhaps you already kind of answered this in your previous answer, but I just wanted to make sure that I got it there. Did you have a chance, or do you believe that with the data that you have, you could understand what type of drift you're looking at? Or let me just tell you, so maybe what type of data set shift you're looking at, whether it is a covariance shift, whether it is a label shift, whether it is proper concept drift. So instead of looking at whether it's a sudden, gradual, incremental, recurrent drift, I'm more interested in the type of drift that you can look at, because that would suggest you some way to focus some research direction. So is it that is the cause of most of the drift we look at of covariance shift, then we can look at KL divergence, for instance. I don't know, like some way to kind of direct some research direction.
Yeah, I agree. But I think machine learning community has some kind of KL divergence when evaluating the distribution shift. But unfortunately, I think it's hard for the security community, because in the real world, oftentimes we don't have the labels for the testing set, and it's very time consuming to get those labels. So I think those KL divergence distribution shift is much harder to deploy on security data sets. And as I just mentioned, I think we briefly discussed the two types of concept drift. One is in-class evolution, means that benign could evolve and malware could also evolve. But unfortunately, I don't think we have ground truth for that, means that we don't know which sample is really an evolution. And another type is unseen family. This setting is easier if we can label the sample and we can know that it's from a previously unseen family. Did that answer your question?
Yeah. Thanks.
Thank you. By the way, great question.
Thanks a lot.
Okay, so it's almost 3 p.m. California time. I'd like to thank you again, Limin, for presenting. So we're going to take a 30-minute break, and then we're going to come back for the last session of the panel in exactly 30 minutes, 3:30 p.m. for an hour.
Yeah, thank you so much.
Absolutely. Thanks, Limin.
Yeah.
Round of applause. Thank you.
Yeah, the panel should be very exciting. We have it's going to be a really nice panel on sort of generally security and beyond the things that we normally consider of just LP norm adversarial examples, like what should we be thinking about, and it should be very nice. So please do come back and we'll see you all in 30 minutes.
Okay.
Perfect. Okay, so I guess we have Nicola who put together the panel, who's going to introduce Ram, who then is going to introduce all of the panelists who are then going to talk about their wonderful work. So Nicola, please go ahead.
I don't know if we just lost Kamalika. Just want to double check, but I can start.
She's coming. Yeah, no, she's coming right through back in.
There you go. Okay, perfect. Awesome. Well, I'm very excited to introduce Ram today. We organized this panel together with Reza Shokri. And the idea behind it was to explore a little bit of broader set of topics, sort of around trustworthy ML, and in particular in areas like privacy, fairness, and ethics, in addition to sort of the typical security angle that this workshop takes. So today Ram is joining us. He's in the Azure Trustworthy ML team, and his work has been broadly trying to understand how the research that we're doing, all of us in this community, how it applies to production pipelines in the industry. And I know he's spent some time in the past at Harvard trying to also figure out the legal implications of machine learning. So he has a very broad perspective of the question that we wanted to address. And last year, I guess Ram organized one of the first virtual panels that I attended in the pandemic at ICLR. And he did a terrific job. So I'm excited to see what we'll have today. And we're joined by an amazing set of panelists, Aleksandra, Anupam, Kamalika, and Seth. But I'll let Ram introduce them. Please take it away, Ram. Thank you.
Yeah. First of all, thank you for the generous introduction, Nicholas. I am actually very excited for this panel for a couple of different reasons, least of which that trustworthy machine learning is really now an umbrella term to kind of like describe like machine learning systems, right? Is it fair, explainable, robust, privacy preserving? And what we really have here is a panel of luminaries who've kind of like looked at this trustworthy machine learning from different perspectives. In preparation for the panel, I had the wonderful joy of reading like Kamalika's work that really looks at privacy and fairness in the context of like explainability, like how Anupam was looking at it from a very similar perspective, but explainability and robustness. And Seth, I'm going to dig so much into model unlearning. Thanks for also sharing that perspective. So, and finally, Aleksandra's work really ties all of this together with her like really path-breaking work that she's done and applying it to like Snap and like auditing Facebook and like grounding this in like Apple's privacy controls. So we have these like amazing mix of people who are grounding things in theory, but at the same time, this panel has also had this amazing experience of actually applying this in the real world. So we're gonna like, this panel is just, I've got like a list of questions that are prompts, but if you have questions, please kind of put them in the chat. Nicholas, like, I'm hoping that you'll be moderating the questions. We will definitely like, as we're having these conversations, weave in the questions from the audience as well. So this whole panel, I've kind of like divided into three parts. The first one, we're going to think a little bit about like what are the trade-offs, and then a really deep dive into like machine learning, and spend a good amount of time thinking about what should we be discussing in like the 2022 version of this workshop. So it's going to cover a lot of different like aspects, and I'm hoping you'll be joined over here. So please, if you have questions, please put them in the chat. Nicholas and Lorenzo will be kind of like flagging me for this. I'm not going to be looking at the chat window, but they're going to be there. So with this kind of broad introduction, Kamalika, I want to start with you. You gave a really riveting talk recently at MIT LIDS, and you laid out the relationship between like privacy, accuracy, and data in this like neat little triangle. Can you talk a little bit more? Can you just recap that? I think it's a great framing for this panel.
Okay, thank you. So this is, kind of what I have been talking about for quite a while, and I think it's that's kind of what people expect. So in the differential privacy world, and also, it also applies to other kinds of privacy, which we'll get to in a little bit. What happens is that the relative loss in accuracy due to privacy is, there's no privacy accuracy trade-off. It's more like a privacy accuracy data set size trade-off or number of people trade-off. So if you have enough if you have enough people in your data set, it's very easy to, you can get both privacy and accuracy. So I'll give you an example. Let's say you want to calculate a sample mean with privacy, right? So what you would be doing is, if your data is bounded, you would be adding noise proportional to one person's value. Now, if you had 10 people, then obviously you wouldn't be able to get good privacy and accuracy. However, if you had 1,000 people, then you can have both.
Absolutely. And Anupam, like the reason why I kind of like asked Kamalika to kind of like lay that off is, looks like there's always going to be trade-offs that's going to be happening in the context of like trustworthy machine learning. And we're going to explain that in a different angle. You kind of recently published a work in Europe kind of discussing one of the trade-offs. How does this between explainability and robustness? It had a very interesting link to this, which I think our audience might find very interesting.
Yeah, thanks for that question. And much like Kamalika was saying, sometimes it's not a trade-off. You can have your cake and eat it too. And it's exactly the same kind of result here between explainability and robustness. Interestingly, and some of this goes back to some work from Mohammadreza's group as well at MIT. There has been a sequence of results where people have looked at explanations. So imagine a deep neural network, it's doing some kind of image analysis task. And much like Nicholas has been, both of these Nicholases who are on the call, they go around attacking predictions and make a pig look like an airplane or something like that. There has been another interesting body of work doing the same kind of thing, but on explanations instead of on the predictions. So a llama still looks like a llama, but the neural network is not focusing on the face of the llama, it's focusing on like the background or some random thing, which shouldn't really be the reason why this image should be classified as a llama. So there's a series of papers discovering these kinds of attribution attacks, which are somewhat complementary to the prediction attacks that the Nicholases and a bunch of other people have been doing in their spare time. Now, when that happened, the community kind of perked up a little bit and started trying to, some of the conclusions in that line of work is, hey, the attribution methods are broken, the explanation methods are broken. And that, turns out, was not the right conclusion. Actually, the problem was not with the explanation method. The problem was with the models themselves. The models were not very robust. And so there was a very diffuse set of factors why the image was being classified as a llama. So what this paper shows, and there's some other work in this neighborhood as well, is that if you actually make the model more robust, then your explanations also end up being much more meaningful. So that, and that connection between robust models and explanations is a little bit like what Kamalika was talking about, privacy and accuracy. It's not like you have to give up one for the other always. In certain cases, in her case, what she was pointing out is that if your data set is sufficiently large, you can have both. And what this result is showing is that if your models are sufficiently robust, then your explanations are actually going to be more meaningful.
And Seth, you think you're agreeing, like, how do you look at it from your perspective?
How do I look at sort of just trade-offs generally?
Yeah.
Yeah. I mean, I guess, there's two sort of worlds where I look at those trade-offs. One is this privacy, accuracy trade-off or lack thereof. And then there's the fairness in machine learning setting where I would describe it as more of a trade-off, where you generally have some sort of unconstrained machine learning problem and you're trying to impose some fairness notion, whether it's an individual fairness notion saying, two individuals should be treated similarly, or you're trying to equalize some statistic of the classifier over a group, over protected groups. But I mean, whenever you introduce a constraint in a learning problem, your accuracy is necessarily going to go down, although in many cases, not by as much as you would think. I think one thing about that I think is key to make is, the fact that the accuracy is going down when you're making the model more fair is predicated on the assumption that the data has been collected in a way that is not biased itself. And so that is probably a very incorrect assumption in many of these settings. And so I think you probably can be learning a better model while equalizing some of these fairness notions as well. In terms of a privacy accuracy trade-off, I definitely agree with the perspective that Kamalika was sharing. One thing I would add is that privacy can also confer additional benefits beyond sort of like in-sample accuracy in terms of generalization. And robustness as well. So that's another example where you can kind of have your cake and eat it too, in that if you train a model with differential privacy, you naturally have guarantees against overfitting. And so this is this line of work called adaptive data analysis, which studies that kind of solution.
So looks like.
Sorry, so I just wanted to add that Reza had a paper in the opposite direction, right? That if you have more robustness, then you might have less privacy.
Oh yeah, hello everyone. Yeah, so that robustness was actually computed with respect to the adversarial examples, right? Not with respect to data poisoning. So when we consider robustness with respect to data poisoning, then it's consistent with differential privacy. Whereas a class of algorithms which are used to make the model robust against adversarial examples make the model more dependent on the training data. And that could be exploited because it makes the decision boundaries of the model around the training data have a different characteristic compared to that of test data, and an adversary could exploit that.
Yeah, I mean, I was about to ask the same question, Kamalika, because I'm so glad that Reza, who also won the Time of Test Award, is also over here. So it's great that we can just like pull in all these experts by cold calling them. I want to get like Aleksandra involved in just a second, but Kamalika, one of the things that actually is very surprising for me is how your work on R separation kind of said that you can have both robustness and accuracy. There's not really a trade-off. How did people perceive that result when you first published it?
Well, so what we are saying is that there shouldn't be a trade-off in principle. Because in general there was for a while there was a belief that robustness and accuracy might be inherently at odds with each other, and what we showed is that a lot of popular image data sets are actually separated enough, right? They're well separated enough in space. Their test and training distributions are well separated enough in space that there exist smooth classifiers, there exist robust classifiers that will separate them. And not just that, we even did some experiments where we were trying to fit the union of the training and test data into models with the same architecture. So it's cheating in some sense. It's just an existence result. It's not, algorithmic result. And we found that we could do that perfectly, right? So there exists a model with the same architecture that you are normally using, which could perfectly fit the training and test data robustly. But when you try to fit the training data using the standard training methods, they don't generalize. So our conclusion was that the generalization process is what is blame. So it's not an inherent thing, but that's what we really need to focus on. Why are the adversarially robust models not generalizing? Not that, it's not a fitting problem, it's a generalization problem.
We can just blame it all on the algorithms. It's bad algorithms, I agree. I want to get Aleksandra in. Aleksandra, among the many things that you do is also, I know you work in the intersection of AI and policy, for somebody who, like you, works in this trustworthy machine learning field where there's so many trade-offs, but now you have these legislation and standards and things like that cropping up. How are people wrapping their heads around this trade-off in a meaningful fashion to create meaningful policy?
That's a great question. I think it's a hard thing to around this, because if for a long time people thought about trade-offs like you can either have security or you can have privacy, you can have both, or you can either have privacy or accuracy and you can't have both, then it's something that is very challenging to overcome, right? Like this conventional wisdom. So I think actually it's on us, on the technologists, to kind of reimagine that this conventional wisdom can sometimes be challenged, and to show in what ways it can be challenged and how one can have your cake and eat it too, like Anupam put it. So.
And do you think we're there? Do you think like the current legislation that you're seeing, do you think that kind of are we heading in the right direction, Aleksandra, in your opinion?
I think we're heading in the right direction in the sense that there's now that policymakers are paying attention to these issues. And it's pretty clear that not everything can be done by the companies self-policing, and that we will need to have some policy around it. So from that perspective, I definitely think we're heading in the right direction. In terms of the specifics of how the policies are written, I think many have still a long way to go in terms of understanding what is the state of the art computationally and thinking through how to translate that into policy. And kind of on the flip side, I think we all still have a lot of work to do in articulating what can be done and how these trade-offs can be viewed not necessarily as trade-offs, or when it is necessary to make trade-offs, and being very clear about that for specific use cases, for specific machine learning models, for specific robustness notions, fairness notions, privacy notions, and so forth. So I think both sides have a long way to go still.
I mean, that's a great, on that note, I want to ask Nicholas, any questions from the audience that we want to?
Yeah, I was actually going to interrupt, so we're perfectly in sync.
So
there's a question, actually two questions in the chat that are related to this discussion that everybody has been having around the possible tensions. And the question is, do you believe differential privacy might be the solution to build models that are both robust and private models? So this is, I guess, a billion-dollar question. So I don't know who wants to take that.
Kamalika, do you want to start?
Well, one of the things that I'm trying to say for a while is that privacy is very context dependent, and differential privacy is the answer for a lot of very good privacy questions, but not for everything. Right. And so when you say the answer to private, I think you have to, so you have to say, what do you mean by privacy? Is it location privacy? Where for location privacy, it's not exactly the thing. And, so depends on context. It's very context dependent. For robustness, I guess what I think a lot of people have said that differential privacy does defend against things like data poisoning attacks, but for things like, adversarial robustness, it's not clear how it does. So I think we would need both, right? I mean, both privacy and robustness solutions, and we would need to understand how they work in combination with each other.
Awesome. Anupam, do you have, I know you've been working in privacy for a long time as well. Do you think differential privacy is the solution?
I think I found from having hung out in a bunch of these meetings in the past is it's usually safe to agree with Kamalika.
Yeah. I love this. Oh, you're all fans here now. That's amazing. That's awesome. So I'm now going to move to the second part of this discussion, thinking a little bit more about fairness and privacy. I want to actually start with Seth, you wrote a really thought-provoking article in Wired a little while ago. It was entitled like, Facebook's racially targeted ads aren't as racist as you think, which I think is a very like thought-provoking title. Can you talk a little bit more about that?
Sure. Before I go into that, I do want to make it clear that when you write these op-eds for popular things, you don't actually get editorial control over the title. The editor picks the title. And so I did not pick that title, and it's actually almost the opposite of what.
Yes, exactly. Yes.
And so that was a good learning experience for me. But yeah, I'm happy to give the background on that, and then I'm going to hand it over to Aleksandra because she is really the expert in this area.
Exactly.
So this is back in 2016, and there had just been this ProPublica report on how Facebook's advertising platform allowed advertisers to target their ads using like ethnic affinity filters, and there was a lot of furor over that, probably rightly so. And the point I was trying to make was that not that the fact that they're using those filters means that their algorithms aren't racist or biased like the title implies. What I was saying is that in general, auditing algorithmic systems with respect to fairness is a lot more complex than just whether or not race or any other sensitive variable is included in the algorithm. And in fact, in both toy and real world examples, oftentimes you need to include sensitive information in the data set in order to build a fair algorithm. And the reason for that is because, you know, covariate and outcome distributions differ in reality among sensitive groups or in the training set, whether for many different reasons: data collection, measurement, just, you know, actual differences between populations. And so if you want to equalize those results, outcomes from the classifier, you actually need that information to incorporate it into the algorithm. So that's kind of the point I was making. And then I concluded by saying that what we shouldn't be looking at whether or not they include those variables in their system. We should be trying to push them to, build a more transparent, advertising platform where they're actually collecting metrics that are meaningful, about the inner workings of the system, and reporting those. And haven't followed it enormously closely since then, but it seems like that's not what they did. What they did was actually just limit kind of the ability to target some filters. And per Aleksandra's recent groundbreaking study, it seems like those issues have not been solved. But maybe I'll hand it over to her to talk more about kind of the current state of Facebook advertising and bias.
Absolutely. Aleksandra, your work was particularly insightful because it was cited in Facebook's civil rights audit report. I would love to kind of how you look at this problem and where are we in current state of things.
Seth rightly pointed out that advertisers can sometimes create discrimination by using Facebook's ad targeting tools and selecting people based on affinities, ethnic affinities, or gender, or age in contexts where they're not allowed to use those characteristics. And what we've been doing with colleagues at Northeastern and Upturn and now also at USC is really trying to understand, assume that the advertiser is trying to reach a broad and diverse audience. What is the role that Facebook's algorithm plays in then delivering these ads for creating possibly discriminatory outcomes? And of course, we don't have access to the algorithm or to the data that Facebook uses. And so what we're trying to do is really come up with ways that one can audit such an algorithmic system in a black box manner without any special access, only the access that a typical advertiser would have to the system. And we think that these questions are particularly important for opportunity ads, such as job ads, loans, housing, etc., because those ads really moderate exposure to opportunities. But in the broader picture, auditing the ad delivery algorithm perhaps can also tell us things about other algorithms deployed on the platform, such as like the newsfeed ranking algorithm. And we can imagine that some of the same components get reused in a lot of the pipelines. So if the ad delivery is discriminatory, then it's quite likely that also the ordering of the newsfeed may be discriminatory or may be emphasizing not the things that are societally beneficial. And so what we found through a series of experiments, and you kind of have to go through a lot of careful design choices to control for things like whether particular audiences tend to use Facebook more or less, or to control for things like market effects, which is the other advertisers on the platform. But what we found is that really Facebook's ad delivery algorithms play a significant role in deciding the outcome along gender and racial lines. So, for example, for jobs, even if the job advertiser targets the ad to a gender diverse audience, what tends to happen is Facebook tends to deliver these ads more to the gender that is already kind of dominant in this profession, rather than in a balanced way. So to give you just an example, most pizza delivery drivers are men. Most Instacart delivery drivers are women, even though the qualifications for those two jobs are exactly the same. You need to know how to drive a car, right? But because in the real world, that's the skew. Now, if you advertise for a pizza delivery job, then most of the ads will go to men. And if you advertise for an Instacart delivery, more will go to women.
Can I ask a follow-up question? So I like that you're approaching the problem from an external auditing perspective. Do you think there is any way that we could, and I think others on the panel will also want to chime in, sort of to design algorithms in a way that they're easier to audit? So is there some sort of proof that the company can provide to an external auditing, or to facilitate the external auditing by changing the way that they design and they implement the algorithms?
That's a really great question, and this is exactly the question we're working on investigating right now, and hopefully I'll have an answer in the foreseeable future. I think it would be a really, if there was a way to do that, then it would be a really good compromise between requiring the company to reveal the algorithm or reveal their data, which is frankly not possible from the business perspective, and this kind of ad hoc analysis that one can try to do from outside but can not necessarily do reliably. So I think if there was a technical way to do this, it would be a really fantastic compromise.
Any questions from the audience for this section?
For this section, there is a question that was asked sort of just as we switched topics. So I don't know if you want to circle back or not.
Yeah, and we can ask that right now before we move further along the
So the question is coming back to sort of the differential privacy discussion that we were having before, and sort of whether there is a way to overcome the privacy implications of increased robustness to adversarial examples. So I guess this is a follow-up to what we were discussing previously with sort of the tensions between privacy and robustness, and some of the work that Kamalika mentioned that Reza has been looking at as well.
Yeah, I feel like it's a particularly hard one. Reza, do you want to take that?
Yeah, so this is a very interesting and technically challenging problem. Some direction that maybe we can look into that is that using public data has been shown to be helpful in improving the trade-off between accuracy and privacy. And also using public data has been shown to be helpful in improving the relation between robustness with respect to adversarial examples and the generalizability of the model. So that could be one intersection that I see in terms of the techniques that could be used that make the model more, just we have a triangle here, the robustness with respect to adversarial examples, privacy, and accuracy. And it seems making use of public data in the right way might be helpful, but still I'm hoping that there would be better techniques that by design are more privacy preserving and more robust with respect to input perturbations.
Anybody else has any other thoughts on this? Okay, so thanks, Reza. We'll now move to the third part, about like machine unlearning. It's only a matter of time when, when somebody puts out the data set, rightly so, there's more investigation that happens. Like, for instance, when Microsoft got the MS Celeb data set, it had a lot of problems and was kind of like yanked off the internet. But now the question is like, what does it even mean to delete data from a model? And is there even consensus for data deletion? Seth, I know you've looked extensively into this. So do you want to start off with unpacking machine unlearning for us?
Yeah, sure. And I'm definitely in the company of a number of others who've looked at this problem, although it's very early days. So maybe I'll just give a quick sort of background in terms of where we're at. So I think one of the main drivers in terms of this machine unlearning problem, or equivalently a data deletion from models, is recent regulation. So in GDPR in Europe, or CCPA in California, or there's a Virginia privacy law, all of which give users the right to delete their data from companies and confer pretty widespread powers to the regulators to find companies that don't comply with supporting the so-called right to be forgotten of users. Mm-hmm. And as a long line of work has shown, we're all aware that not only do databases contain our personal data, but personal data can be exfiltrated from models. In an obvious way, like a kernelized support vector machine that literally has support vectors that's part of the model. Like, obviously that contains personal data, but also through membership inference attacks and increasingly sophisticated ways of learning about the training set. And so even regulators are starting to come around to this point of view that models could actually be considered personal data of participants in the training set. So the European Information Commissioner's Office has said that if somebody wants to delete their data and it's been used in training, that this may actually require full retraining of the model with that user's data. So you would have to delete the person's data from the training set and then totally retrain the model. And so this is in place for machine unlearning, which says, clearly this procedure would constitute deleting somebody's data from the model, like they weren't in the training set, but it's probably very impractical for large data sets, and when the number of deletion requests can be very frequent. And so can we trace out an algorithmic middle ground between this possibly impractical but definitely privacy compliant baseline of fully retraining the model when somebody wants to delete their data, and this exceedingly practical but possibly illegal current standard of not retraining the model at all? And so early work has studied this problem in a variety of contexts. The current definition that has kind of been adopted seeks to essentially bound the distance between the distribution on models after fully retraining and the distribution that a machine unlearning algorithm can induce on the model. So rather than fully retraining, we just want to get close to the distribution we would have gotten if we retrained, but hopefully with a lot less computation and comparable accuracy. And so the first paper that used that definition was this Making AI Forget You paper in 2019, which studied k-means, I believe, clustering. And there's been a number of subsequent papers that use a similar definition in supervised learning. So Kamalika has a great paper on approximate data deletion from linear and logistic models that uses a really cool like leave out points and use the predictions to sort of tweak the model trick, which maybe she can talk a little bit more about, but gets the best current bounds for deleting data from linear models. I've studied both deleting data from just generally strongly convex models, and then there's been and convex models where you kind of regularize. The insight there is essentially want to delete a point. Delete the point from the training set, take your previous model, and then take some gradient descent steps with respect to the new data set that has the deleted points removed. And if the model is strong, if the objective function is strongly convex, you know that your new optimal point is close to where you're already starting. And so you can obtain results in that manner. There's also some pretty cool work that starts in the non-convex setting with like a pre-trained model and then fine-tunes a convex model on top of that and uses similar techniques to delete points from that model. And then in the non-convex setting, there's this machine unlearning paper, which Nicola is a co-author on, which uses distributed techniques where essentially, well, actually, why don't I pass it to him to describe his own paper?
We were not supposed to sit on the panel, but that's okay. So the intuition is twofold. The first one is to reduce the number of parameters that are involved in the retraining by sort of splitting the data and training smaller models on the distant sets of data. And the second observation is that you can change the order in which you introduce the points during training. And then this allows you to save useful intermediate states of the model regularly before you introduce new data into the training procedure. So for instance, you could imagine training first on 10% of your data, then saving a model state, then adding another 10%, continuing training, saving another state, and so on. Then you can revert back to the last state that you know before you introduce a specific point that is to be unlearned. And that allows you basically to make the naive retraining algorithm a lot faster.
I mean, that's super cool, Nicholas. And Seth, thanks for sharing this. Kamalika and Anupam, this is like a question that, of all things, that we started off with, what's the connection between like machine learning and differential privacy? Is that something like an obvious thing that I'm just missing, or just because I'm not familiar with the field? Can you tease that out for me a little bit?
So machine unlearning is, it's definitely easier than differential privacy. So differential privacy, if you train something with differential privacy, it would be robust to indistinguishable for unlearning 1 point, right? And if you are unlearning k points, group DP will be, it will be indistinguishable with k epsilon. So it's definitely a stronger notion of privacy. There is, I believe, a recent preprint by Gautam Kamath and their group, which show a much more clearer, map epsilon. And that's, of course, for a specific algorithm. They show up, it's maybe epsilon DP and epsilon prime unlearnable, where epsilon prime is much better than epsilon. But my understanding is that it's for this specific algorithm.
Okay. Anupam, do you want to weigh in here?
I think the sufficiency of differential privacy for the problem is clear, because it's providing that guarantee for all inputs. Now, if you're only interested, and this is where I have more of a question rather than an answer. But my question here is, if you're interested in unlearning for some specific subset of individuals, as opposed to having the kind of universal differential privacy guarantee, can you do anything better than differential privacy? Is anything known on that? Nicholas, have you or Kamalika, have you guys worked on that problem? Have any insights to share?
No. It's an excellent problem.
Yeah, no, I completely agree with you. That is actually something we wrote up in the introduction of our paper, where we say basically DP is somewhat orthogonal to unlearning because you care only about a specific point in unlearning. And so you would have to basically show that you have an epsilon of 0 for that specific point, which is sort of an overkill to use differential privacy for, because obviously you wouldn't be able to learn anything. So I would treat them as orthogonal unless you're sort of using approximate approaches where you're trying to bound the error term on sort of the unlearning process. And then you can imagine that, yes, with differential privacy, you're basically getting some worst case guarantees about what this error term will look like. But for the sort of the exact retraining approach, and I think this is why I'm actually going to ask Seth if you can paste a link to the statement from the Office of the Information Commissioner that you mentioned. Someone asked for it in the chat. I think people will be very curious because it's unclear sort of what will be policymakers' perspective on what satisfies sort of the requirement for having unlearned a point. So I'd be also very curious to read that statement.
Yeah, another thing that this brings up in my mind is some of the overfitting related problems, which then lead to membership inference attacks. So if you think about those kinds of examples, I think Matt Fredrickson and Klaus Leno have this interesting paper called Stolen Memories at Usenix, which some of you may have seen. And they have this interesting example of how the neural network is able to identify Tony Blair's face, not based on his facial characteristics, but this pink background, which the network has learned at that particular concept. So that's an example where the network has learned something very specific. It has memorized something very specific about the training data, which it's then using in classification. And some of the explainability work can help surface that kind of information, as that paper shows. These white box attacks are leveraging that. And what that kind of train of thought leads me to wonder is whether that naturally leads to some fixes or adjustments to the model, where maybe there are parts of the model you can trim off to erase the information that is specific to very specific training instances. It's going to be tricky. It could be tricky if the representation is much more distributed. So there's more to think, or maybe there's some form of directed regularization one could do. But this kind of returning back to returning back to this question of how to unlearn in a more targeted way. And then it's more of a direction for exploration, where the thought is there might be something that's feasible, leveraging internal explanations that surface overfitting. And it won't work under certain conditions of concentration effects and such, where a lot of the information is in a small part of the network. I wonder if there could be a way forward.
Yeah, onto this this question around the connection between differential privacy and machine learning as well, sort of from a completely different angle. So like Nicola was mentioning how, so in his paper, it's an exact unlearning algorithm, meaning that you get exactly the distribution that you would get from retraining. There's an important note about that though, which is that it's only an exact unlearning algorithm. In fact, it's only has any guarantees in that CISA framework if you assume that the points that are being deleted are selected uniformly randomly, or not randomly, but independently of the output models. And that's actually a pretty strong assumption, because you could imagine that whether or not people want to delete their data is actually very adaptive to the released models. It's like, these models are released, and then there's some Wired article about how, these, personal training data can be exfiltrated from that model, and then that, makes people in a certain subset want to delete their data. And so there can, in practice, be this adaptivity between the points that actually get deleted and the output models. And so that's one point where, when you have the choice of almost like an adversary deleting points that can play off the internal randomness of the algorithms, one way to defend against that is by training using differential privacy. So that's a completely different angle, but it's using this connection between differential privacy and adaptivity, and saying that if you actually make privately in the different shards in the CISA framework, then you can prove that any adversary who can choose any points to delete can't pick points that induce a training distribution that's different from retraining. So for example, in terms of like how you could do such an attack against CISA, one thing you could do is, like, supposing that all the models were published every round when you're deciding what points to delete, you could exploit the overconfidence of those models on points that they were trained on, and use that to only delete points that came from the first, like, let's say, 5 of 10 shards. And then if you looked at the accuracy of those shards versus the accuracy of the shards 6 through 10, those shards would have a much worse accuracy. But of course, under retraining, the points are assigned uniformly randomly. So like the probability that those shards would be more accurate is always 50%. And so like that creates a separation essentially between it proves that it doesn't have a theoretical deletion guarantee. So that's something that I'm looking at with a number of co-authors at the moment.
Well, when it materializes, you heard it here first in this panel with Anupam's and Seth's work here. So I'm gonna we have 8 minutes remaining, and I wanted to take a step back and kind of zoom out a little bit. And Aleksandra, I want to start with you. How has COVID changed, do you think, the game for privacy research? Do you think it's had an impact? Do you think people are just going to continue working on the same things they worked before this? What's your take on this?
I don't actually know.
Yeah.
I haven't followed what is happening in privacy preserving contact tracing, although I know there's good work happening. So I don't know how that will impact the privacy research.
Or in general, the work that you do with auditing algorithms and things like that. How do you think COVID's actually had an impact on this? on the work that you do and the work that you kind of generally like flourish in.
So, one impact is that none of the privacy researchers now talk to each other because of COVID.
Yeah, that's a great outcome. Hopefully not.
Yeah, maybe like sometimes when I get a question and I don't know the answer to that question, I answer a different question. Is that okay, Ram?
Totally. Go for it, Anupam.
Okay. So one thing that COVID has had impact on in the broader space of machine learning and trustworthiness is that models have gotten more wonky, if you will, or, the world has changed. When the world changes, models don't always behave the way they used to behave when they were trained. So that's something we have seen a lot of during COVID because the data, the production data looks a lot different from the training data. And also some of the relationships which were perhaps stable in a normal world just went out the door. Like Kamalika said, people are not meeting each other. They're driving a lot less. What does that mean for auto insurance pricing models, for example? It's very, the production data looks very different. So stability of models, which is an important part of trustworthiness of machine learning, that's an area where there's a lot of interest because the world has suddenly changed and it doesn't look at all like what it looked like when models were trained. So that's one area where I would say within the space of trustworthy machine learning, there has been broader recognition of the importance of this kind of trustworthiness attribute and having methods and tools that can be reliably applied to both understand if the model behavior is very different, why is it different? Is the model still going to perform well in production? If it's not going to perform well in production, what's the reason for it? What needs to change? So a whole host of questions in that neighborhood are getting more attention.
So if I may add, I think this is a great point. Some other observation is that basically the number of samples that now different organizations have about this new data distribution is much less than the old data that they had. And that increases the demand for data sharing among these organizations and makes the now connecting it to privacy, but they cannot share the data. And therefore, it has increased the demand for using and implementing various federated learning or decentralized learning algorithms that they didn't care to implement before because they had lots of data internally. Now, when the trend changes, then you need to pull all the data together to be able to come up with something more valuable. Yeah.
Absolutely. I mean, that was a way better question and phrasing. Thank you all. Nicholas, any questions from the chat before we wrap up?
One question which is asking what happens when people share data points. For instance, if they live in the same address. So I'm guessing this ties back to the discussion we were having on probably unlearning. It was asked about 6 minutes ago. It's missing a bit of context. Will, if you want to clarify, I'm happy to read the clarification part.
Sure. We have like 3 minutes remaining. Okay, so we'll try to wait for that clarification. Else, I'm sure the panelists are going to be hanging out a little bit after the panel's over. So, as we wrap up, if you all as panelists had the opportunity to shape people's research agenda, what topic do you think we should discuss in the 2020 2022 Deep Learning and Security Symposium next year. I'm going to start with
so before we go to that question, so I got the clarification. So it was indeed about unlearning, and I guess the question is asking essentially if two people have the same data record, and one of them asks to delete the data record, how do you sort of go about unlearning? So I guess there are two ways you could approach the 2 points sort of as being flagged for unlearning, or just unlearn one of these points. And this will have sort of different modeling assumptions about sort of what constitutes your data and what is the general distribution that you're trying to model, I guess. I don't know if you want to comment, Seth, because I think this is sort of related to the intersection with fairness that you brought up.
Yeah, I think it's challenging because I guess the user who's deleting their data is asking to be protected from, you know, the model making inferences about him or her, you know, based on other people's data, which is a tricky sort of protection. And, you know, it seems like a rabbit hole to go down where I can delete my data and thereby force you to delete your data just because you can infer things about you from me. And so, you know, it's probably very context dependent, but it seems like it would be dangerous to just automatically kind of delete linked data without proper consent.
Yeah, this reminds me sort of the discussion around sort of the fact that differential privacy doesn't prevent you from sort of general facts that are in the distribution. So it won't prevent the model from inferring that you're more likely to have cancer if you smoke or something along these lines. So I think this brings up sort of a similar question, but in the unlearning context.
Yeah, exactly.
So I guess, Ram, we won't hijack your conclusion question anymore.
Oh, no worries. I just want to get the panelists' thoughts on like what do you think people should be working more on? Aleksandra, do you want to start, and then we'll just go around the block and conclude?
Sure. I think all the topics we've discussed are going to be worked on in the next couple of years by a lot of talented researchers, and I think they're all very important to what we may be discussing in addition in 2022 is perhaps the question of incentives. And maybe going back to the trade-offs and whether you have to make trade-offs, perhaps we'll be also talking about what is the trade-off between privacy, fairness, robustness, explainability, and whatever is the financial purpose that that model is being used for, and the financial impact of achieving some of these desirable societal properties.
Absolutely. Thank you, Aleksandra. Seth?
Yeah, so since we're wrapping up, first of all, I just wanted to thank Nicola and Reza for inviting us to this panel, and Ram for moderating. I think one of the things I'm most excited about gets to this question about if differential privacy is like the solution. And I think that there's a lot of exciting work to be done to sort of bridge practical gaps when you try and apply differential privacy, but also in circumstances where differential privacy isn't a great solution. For example, in like a high dimensional genomic analysis where you have hundreds of thousands of queries you need to answer and differential privacy is just too stringent and the stakes are maybe too high. What intermediary sort of privacy measures can you, propose and, still kind of have theoretical guarantees where you also get, reasonable utility. So rather than, fully heuristic approaches, sort of approaches that are well grounded in theory, kind of information theoretic privacy guarantees to be applied more widely is something I'm interested in. And I think the solution might revolve around sort of a more realistic modeling of the adversary in differential privacy. So differential privacy is such a general guarantee. It really applies to any prior belief for any adversary and handles all auxiliary information, when in certain application domains, there might be a much more natural adversary. And so can you tailor a notion around that? I think is an interesting problem that I have no idea how to solve.
Thank you, Seth. Anupam?
Yeah, I think for me, what was exciting about this panel, much like Aleksandra said, is the deep relationships across these different attributes, if you will, of trustworthiness. And I'm really glad to see that and at the Security and Privacy Symposium, where often we have historically stayed more sharply focused on security and privacy topics, but these are just at a technical level, fairness and robustness and stability and all of these notions that we touched on today are just so tightly interconnected that in some ways, like, it might be valuable to take this workshop, rename it to Trustworthy Machine Learning or something like that, and have it at the Oakland Symposium. I don't want to make that my plug for next year, but it's something worth considering, that our community is really now a big part of this much broader set of problems, and it might be worthwhile to think about how to reflect that back into the way we name our events and call ourselves. Yeah.
I mean, if it goes by any other name. Thank you, Anupam. Kamalika, you get the last word. As Anupam said, we will just agree with what you just say now. Yeah.
I was going to just agree with Anupam.
What's your final thoughts, Kamalika? Very curious.
Yeah. But more seriously, my thoughts are, I agree with what has been said previously. I think what people would be working more on is bringing these things together, various aspects, robustness and privacy and fairness and interpretability. I mean, interpretability is also another key part of the puzzle, right? So bringing these things together, I feel like people would be doing more of that. And I also feel like people would be doing more of that in the context of specific applications, because different applications might also have their own, properties and constraints, right? For some applications, robustness might be easy, privacy may not be that easy, and so on. So I think that's what people would be doing next.
Awesome. Well, thank you all so much for your time today. I really appreciate Lorenzo, Nicholas, and Reza's help putting this together. And thank you all so much.
Thank you, everybody, for your
Thank
time.
Thank you guys for coming along.
See you guys.
Bye-bye.
Take care.
Bye.
Thank you for the great panel. So I'll say a few words to close things off for the workshop. So I hope everyone had a good time with all the talks. There were some very nice talks. I really liked all the keynotes, and I think the panel was one of the highlights for me as well. So there's not really too much that we want to say. I'll put in a plug that if you're submitting papers for workshops, we're going to have an AISEC submission deadline in a month or two. And so consider submitting to that. That's ostensibly still maybe going to be in person as the first event that people might be able to go to. At least they haven't yet put it online. So we'll see what happens there. But maybe there's a chance people get to meet in person. I hope you all had a great time. And Alvaro had a nice idea, which is if as we finish, if people want to head over to the Meet New People tab on the left-hand side, you can maybe spend a couple minutes just talking with people sort of one-on-one about whatever you feel like. It might be a nice way to end things so everyone who's attending gets to have some nice discussions along with people who've been able to talk throughout the day. So with that, thank you all for the presentations. Thank you to the speakers, and everyone who helped put this together. And we'll see you at some point in the future.
Everyone, bye.